get started a little bit before 1:15. Hi everyone, my name is Erik Hellman. I am a freelance software developer from Sweden. I usually work on Android, but lately I've also started doing web development as well, and this is why I'm doing this talk about progressive web apps using Kotlin. If my voice would happen to disappear during this talk, we should all blame Jake Wharton, because he was the one who made me drink more beer yesterday than I was supposed to. Okay, yeah, so let's move on. So this talk is about the actual cross-platform, where we actually write apps that run everywhere. That's the intention of the progressive web apps. It's writing web applications that can be installed as native applications. So currently, you can do this, or you can install quite a few of these already. You basically go to the website you have and you can install them, and this is an example of Twitter, Google Maps, and Pinterest that you run as installable web applications on your desktop. The same thing, you can also install them on your Android phone, etc., and all other platforms usually that supports PWA today. So the good thing there is that the difference between the progressive web app, we're going to go into details there later, but it enables you to actually write apps that feels and looks like native applications. We do this in JavaScript, or at least that's the runtime where we got to work with. And anyone who here works with JavaScript on a daily basis? Yeah, I guess so. So you also know that there is a lot of opinion about JavaScript, whether it's good or bad. It is what it is. It has its issues, but so does every other language. But over the years, there has been a lot of alternatives to JavaScript. You write in one language and it transpiles over to something else. Anyone remember CoffeeScript here? Anyone used that? That was great. We can't forget GWT, also awesome. Anyway, there's a lot of these, but over the time, kind of like TypeScript kind of won this one, became the de facto language to use instead of JavaScript. And there are several reasons there. TypeScript is a great language. It has features that make it work really well for targeting the web platform. Because types, they are awesome. They're great. And this is why we like the strongly typed languages, because they help us to scale up projects. Now, the way it works with the TypeScript is in many of the node libraries you can find, but also in the web platform itself, you can find files that end with d.ts. It's a TypeScript type definition for that library or for that API. So the entire DOM API is available as a file called like this. So this is the entire type-safe definition of the JavaScript API, which makes it work inside your favorite IDE and stuff like that. And this is great. So we should be able to use this with Kotlin, right? Kotlin also a strongly typed language, pretty much the same as TypeScript. So we should be able to do something like this. This is an example for using the UI framework lit elements, which builds on top of web components. And this is the TypeScript code of that one. So we should be able to do the same thing in Kotlin with something like this, almost. That's the goal. But as we all know, JavaScript can be a bit weird. You can do this. This is a valid JavaScript thing. It either returns a number or a string. Now, TypeScript deals with this in a great way, using something called union types. Anyone here familiar with the union types? Yeah, cool. You all know what I'm talking about. But we don't have union types in Kotlin. That doesn't exist there. So this is a challenge. And this with the union types is nothing strange. You take, again, this lit element framework that I showed you earlier. It actually has this in its API where it returns a union type of either this one or the other one. And this is the thing we have to work around. This is one of the challenges with using Kotlin JS to target the JavaScript platform. So how does it work? Well, you set up your build script first. We use Gradle. You can use Node, NPM, and all that as well. But I'm going to talk mostly about the whole Gradle build system, or use the Gradle build system here. So you basically set this up. You define the Gradle plugin you're going to use for your project, and you define your repositories, and then you have the Kotlin configuration where you say target this, and with this you want to have Node.js support because you might want to use an existing JavaScript library, and you're targeting the browser. The other alternative is targeting Node, so you run on the server side. And then you define your dependencies. So nothing strange there if you are used to Kotlin projects before. So we write our first super simple application where we add a click listener to a button. So the standard library for Kotlin.js has already a bunch of definitions that matches the DOM API. So we got the document, we can call document query selector, pass in a CSS selector there. And since that is nullable, it can return null. We can do an early return if we don't get that one, and then we add the event listener. And for anyone here thinking that we should be able to place that lambda outside there, we can't because there is an optional third parameter. So it doesn't really work in that case. So you run this through the Kotlin compiler, and you get this. Everybody can read this, right? Yeah, so it's a lot of code. Of course it's a lot of code. Let's extract all the unnecessary stuff. So it defines the main function. And you can see that the first thing is it defines a lambda. That's the click listener that we added. And then the actual main function that we wrote, where it builds up the same code that we had before. And the key to the thing here is the final thing there, where it actually calls this main function. So when you have your typical JavaScript file and you include that one, it will evaluate whatever is there. You can just call functions from the root scope of the script, and that will happen. But we don't have that in Kotlin. So what Kotlin.js does is that wraps everything here and then calls the function itself. So progressive web apps. What's different with that one compared to like regular web applications? Well, it's more of like a philosophy around it. So Google has this very nice, I stole these images from Google as well, nice page where they explain it's reliable, fast, and engaging. But it's more about reliable. It should work regardless of your network conditions. So if you're offline or you have a shaky network, it should still load and show data or show UI. It should be fast. It should react as fast as native applications. So the user shouldn't notice that they are actually loading a web page, so they shouldn't be a big blank page at first. And engaging is that it should behave like a native application. And a lot of this already works today on your desktop, whether you're running Chrome or Firefox. We've got some other experts here in the room about progressive web apps that can tell you more about that. But the key components that I'm going to talk about at least is this. It's a web app manifest, which is just a JSON file. You need a service worker. You usually do need a service worker in order to get this offline behavior. And then we have the actual web UI, which is just regular HTML and stuff like that. So the web app manifest, super simple. This is all I'm going to mention about that. It's a JSON file which defines the icon, the name, etc., etc. Once you have this one, it becomes sort of an installable application. Works like this. So if you go to maps.google.com, you open the menu in Chrome, then you see the install Google Maps, and it will install it on your desktop. And it will look like that instead. And then we'll interact with your desktop as every other native application. So if you do Command Tab and switch to other windows, it shows up in that list. So it's not just a tab inside your browser. Service worker, a little bit more complicated. So the thing is, you have your first HTML page which is loaded in the browser. That one includes a script, your application, main.js. And in turn, the main.js loads the service worker. So something like this, HTML. And then in our main.js, if we would write this in JavaScript, it would look like this. We call navigator, service worker, register, and we pass in the URL to that service worker script. And then, because this is promise, you do then or catch to see if everything worked out all right. So in the service worker then, we call self add event listener, on the install and the activate events. So install is basically the first thing, now this service worker got installed, and activate is when it becomes active and can do stuff. And then we can do things like we can intercept all the fetch requests, and we can either deliver local data that we have stored in either the IndexedDB or the cache or the local storage or wherever, or we can decide that we go out on the network and fetch it instead. So it basically works like a sort of a proxy. So the idea behind that is that we have the service worker running between your web UI and whatever it needs to load to show data. So the service worker can make these decisions for you. So how you decide this is all up to you. Different caching strategies. Should we go to the cache first or network first, or and how should we fall back when something goes wrong, and how should we behave when it's offline? So it's all up to how you implement that. Now, in Kotlin.js, how do we do a service worker? Well, again, we need a main function, so we add an event listener to the load event when this script is loaded, and everything is loaded in the main page. And then we say window, navigator, service worker, register. It's basically the same code. So we start there. And yeah, so all that works out of the box. Now, inside the service worker, the other script, basically, you want to install it, and you want to add caching support for offline stuff. So you use the same API, you get the same API there, but the problem is that in order to reach the scope, the service worker scope, the service worker global scope, you need to use self. And that one isn't defined in the Kotlin.js library, because self in the Kotlin.js, in the JavaScript world, is either the window or whatever service worker scope or worker scope you're currently running in. So it's a union type. So you need to define it in this context as what it is for you here. So here you have external val self service worker global scope. And then Kotlin.js will assume that there is a global variable called self that is of that type. And here we do event wait until, which means that don't proceed with installation until you do this thing, and this thing in this case is basically open the cache and add all this URL to the cache. So cache these things. Also, you see that we need to cast the event to an install event, because the event listener doesn't know what type of event it is. So whatever event listener you have, you always have to do that event as and a specific type. Otherwise, it's just a generic event type. Yeah, so this one, the reference to the service worker scope. Now, so how would you implement the actual offline cache then? So we add a listener to the fetch event. Again, cast it to a fetch event. And the fetch event itself has a request. So we take that request, we pass it into our cache, and say, can we find a matching resource for this one? And if it does, if that one is not null, I'll return that cache response instead. Otherwise, call fetch out to the network and get that data. So this is like cache first strategy. So if all your data would be static and would be downloaded, once the application has run once and loaded the resources, it would just use the local stuff. So we usually write applications that call some kind of HTTP API, whether it's REST API or whatever it is. So how would we do this with Kotlin.js in an efficient way? We could use the fetch API and leave it at that and parse the JSON and stuff like that, but it's not very efficient and it's not very Kotlin idiomatic. So we're going to use two libraries. There are going to be more talks this 2 days about these two libraries. So I'm just going to touch upon the very basic in the context of Kotlin.js. So you add the plugin for the serialization library, and then you add the dependencies for Coroutines and for Cater client, the JavaScript version of the Cater client. So our API is this one. It returns a list of kittens. So it looks like that, very simple JSON thing. So we basically have two objects here. We have the root object, which is the root response object, and then we have an array of kitten objects. Using the data classes in Kotlin, we just do this. We define the data classes, and we add the serializable from the Kotlin X serializable library. And the plugin will now generate the JSON adapters automatically for you. So any of you who have used Retrofit before, it works Retrofit and Moshi before, it works in the same way. But this is a cross-platform Kotlin library that works also for JavaScript. So if you want to test this, basically you can get an object in, you call the serializer on the class, a static function there, and then you create a JSON object, and then you can do JSON stringify, and you can take the data and you can call JSON parse to get back the object. So typical serializer library, and you get this nice type-safe integration with your backend API. Now, it doesn't stop there because the HTTP client from Ktor, the JavaScript version of that one, is really nice to work with here. I actually prefer this one for all Kotlin development these days because before Retrofit and all these others, because it's super simple to work with. So you create an HTTP client, you tell it you want the JavaScript version, and then you say, install also the JSON feature for this HTTP client. Now, if you want to call the API, we got the URL there, just call client get and the URL, and I've been explicit here in specifying the type. So now the JSON, the Kotlin X serialization library will kick in here and assume that you're getting a kitten response and do the deserialization for you. So now you got a nice way of fetching data in a type-safe way. So you had coroutines there. You saw that we have a suspend function there. That's because Ktor builds a lot upon the suspending function in coroutines. So how do we do coroutines in Kotlin.js? Well, JavaScript has the concept of promises. So before I used then and catch on the register call here. The register call, when you register a service worker, returns a promise. But in JavaScript instead, I can define the function as an async function, and then I just add await in front of the call that returns a promise, and it will wait until that happens. So that's how we would do it without using the chained then and catch calls. And you can catch exceptions and stuff like that. So it's pretty much the same thing that we do with suspended function and coroutines. So there is a wait function that is an extension function on promise in the Kotlin.js world. We just define our function as suspend, and you get the exact same result. The extension function in Kotlin.js looks like this. It's basically a suspend cancelable coroutine that takes a continuation. So if you're unfamiliar with coroutines, there are many great talks about that. But when we get the unfulfilled call, we call continuation resume. And if something goes wrong, resume with exception. So it basically wraps the promise API in a nice way like this. So finally then, the UI part. So we covered how to set up the service worker, how to make network calls and do deserializations, and a little bit about how the coroutines work. So what you do, if you want to just work with HTML, sure, you can just create a string and return that, or use the DOM API directly, but it's not very efficient. But there is a very nice DSL called Kotlin X HTML. That one allows you to write HTML code with Kotlin code. So has anyone used this one already? A few of you, so yeah. Okay, so basically we start with getting the root node where we want to add our HTML. And there is an extension function on HTML element in Kotlin. And what we do there is just append. And then we have Kotlin functions that match all the standard HTML elements. So h1 will create a h1 element. The tricky thing here that might be new for some of you is the unary plus operator in front of the string. That one basically means append this string to this element. So it just puts the text inside there. I'm not sure if I really like that one, or if I would like to have like an explicit function called append or something. But well, this is how it works now. So it feels a bit unfamiliar if you're not used to that one. If you want to have a regular image, you do like that. And most of the attributes to these tags are available as inside here also. There's also like if there's something missing, you can also define a raw string and append that one, and it will just evaluate what you have there as HTML and add it. Now, this is regular Kotlin code, so this will be the result of it. This is regular Kotlin code, so we could do like this. We have an array, and then we call append, and we create the unsorted list element, and then we iterate over this one, and nothing strange here. We check which index we have, and then we add the CSS class based on whether it's even or odd index for that one. So you can add the CSS classes here as well. If you want to add a click function on each of these elements, you can do that. Currently here it's empty. And then we just add a plus kitten here, which is the string from the list up there. So there is nothing really weird about this in a Kotlin way. The only downside with this one is that you would work directly with a DOM, which isn't very, very efficient. So you would like to have a UI framework. And currently, the only UI framework for the Kotlin JS that is ready to work with, except for this just working with raw HTML, is React. So JetBrains has created a React wrapper. So you just add these dependencies. And these dependencies look a little bit weird. You see the npm there. I'm going to explain what that means in a moment. But you add these dependencies, and it's basically Kotlin wrappers on top of the React APIs. It works like this. You have a class called rbuilder, and you just keep defining extension functions on the rbuilder class, which will return HTML. So instead of writing JSX, you use the Kotlin X HTML library, so you don't have to like mix raw HTML in your Kotlin code. Then you finally call render, pass in the element that you're going to do there, and call the extension function that matches the root of your application. And this would then be just work like regular React code. There is also another option, which is called the create. You probably have heard of the create React app script, which you use to set up a new React project. They have a Kotlin version of that one, and this is when you would work with the npm package manager and all of those things. So you just install create React Kotlin app as a global npm dependency, and then you run create React Kotlin app instead of just create React app, give it a name, and then you're up and running as standard Kotlin, standard React application. Now here you're missing out. You're not using Gradle to bundle all these things, so I'm not sure if this is the best way to use Kotlin for developing web applications, but it's there. So npm packages. How do you add dependencies to JavaScript libraries? How do you use an existing JavaScript library in Kotlin? So, since you're JavaScript developers, I assume you know what the npm packages are and how to install them. And you can use the same thing in Kotlin JS, even if you're having Gradle as your build system. So we'll take this library that I recently used, the JS zip library. Basically, JavaScript library for reading and loading data or writing data to zip files. And you would wonder why we would want to do that, but yeah, there are reasons. Probably if you want to read the content of a zip file, or you want to generate a zip file to the user in your application, this is the one you want to use. Now, this one, JetBrains hasn't created any wrappers for this one, so we need to create wrappers for this one. But first of all, we also need to import it. So in our Gradle script, we need to make sure that the target, in the target section, we call Node.js. Now it will add support for npm libraries. So we can do implementation npm and then we just specify the name of the library and the version. I think the version is optional, so if you don't use that one, it will always fetch the latest. But you should specify that one so you don't get longer build times. So that's how easy it is to import that one. It will use npm in the background to do this. Now, you need to define the API yourself in Kotlin. So the API is completely in JavaScript. There is no type definition from TypeScript that you can use right away or try to convert. So you need to define it yourself. If we go back here, you see that there is, on the JS zip object, there is a function called file. There's also load async. And each zip object has also an async method. So those are the ones that we need in order to load a specific file inside the zip library. And what we do then, we use the external keyword again. So we say we have an external class called zip object. That one will have a function called async, which will take a string and return a promise. And since we don't really know exactly what's inside that one yet, because it depends on the string you type in there. So if you say blob, it will be a blob. If you say array buffer, it will be an array buffer, and so on. So we need to use any there. There's a promise of any. Now, and then we have the JS zip class, and we define the file function, taking a string. But that one we know that will always return a zip object of a promise. And then we have the load async, where we pass in data as an array buffer. We know that we will get a JS zip back. Okay, so we define the API in Kotlin. We don't need to define the entire API, only the things you need. That's the convenient thing about it. So using this one, so I create the JS zip instance in Kotlin, and then I call fetch to fetch my zip file from the server, and I call array buffer on the response, saying, okay, get me the array buffer of the body, and then I call load async on my JS zip object, which will return a promise of a zip file. I'll call file, passing in the file name that I want, and that one will open up. And then I say, now I got that one, and then I finally call async as a blob, and I get a promise as a blob instead. And then I can create the URL object and pass that one into an image and show the image that was previously inside the zip file. Now, this doesn't look super fun because it's a lot of chaining then calls. So you can use coroutines, of course, to do this, even though you use an external npm library. So yeah, so this is great. This is the way you probably go if you're using an existing JavaScript library, importing that one. But what happens in the cases where you find a type where you cannot use, you can't really convert it to Kotlin easily. It's a union type or something like that. Or it's just really hard to map it. So Kotlin has a dynamic keyword. And dynamic keyword will, it's kind of like the magic last resort. I don't have any better explanation. So remember this one, TypeScript thing, where it returns a union of number or string? So how would we implement that in Kotlin? How would we define this function? Well, what we do, oh, I'm missing a slide here. Nice. So what we do in the external definition we have, we add a dynamic as a return value. And that means that when we call this one, if the TypeScript example code that will return dynamic, we get the result, and it's of type dynamic, which means it can be anything. And now we can cast that one to a string if we know that it is a string. So that would work. But the fun thing with dynamic is that you can call pretty much anything on it, and the compiler will say, sure, because we just convert it to JavaScript. And yeah, it's a great way to shoot yourself in the foot multiple times. But yeah, so this is because we need this one in JavaScript, right? We don't have union types, so that's one example. And it might be a very complex API that you're trying to map, and you say like, okay, finally I know I will get this thing here, and that will be a type. So dynamic to the rescue, sort of, for these things. Now, something new that came very recently to KotlinJS is called DoCut. It's experimental. I don't mean it's very experimental. So this is definitely not ready for production use. You enable it by opening your Gradle properties file and saying generate Kotlin extensions true. What this one will do is add a task to your Gradle called generate externals. And that's basically what it does. So what we have here is index.d.ts, and DoCut only works on the TypeScript definitions, files, type definitions files for npm libraries. So there needs to be a .d.ts file somewhere in that library. So it will take this one and read it and say, okay, we got a function that's called leftpad that has either a union type of string or number, length, which is a number, a nullable parameter that can be a string or a number, and it returns a string. The good thing with having union types as function parameters is that we can map that to Kotlin. And the way DoCut will do this for us is basically generating this code. So this is all the permutations of the leftpad function in Kotlin. It will automatically generate those for us. And this is great. So as long as the developer of the JavaScript library has type definitions defined and added them to their package JSON file, DoCut should be able to pick this one up. Now, it doesn't work completely. There are some gotchas there. And if you try it today on a larger library, more complex library, it probably will fail for some reasons. But at least you can see this code generated, so you can see that they have come a long way, actually. Okay, I am very fast. So is KotlinJS ready for production use? Well, it depends. Some things work really great. Other things are a little bit awkward to use. The current build system will output one single JavaScript file. So if you're going to use a service worker, you have to find a way to work around that one. I excluded my very hacky solution here because I think that JetBrains will fix that soon, so you can actually output a separate service worker JavaScript. You could do that using 2 separate modules, but then you get a large code base because you duplicate a lot of code. Summing up this thing, JavaScript output when using KotlinJS can be very big. This can be an issue, but it could also be fine. Might turn out not to be so much. But also, of course, JetBrains is continuously working on this one, so I expect that to reduce the output a lot in the future. There is also something called dead code elimination that kind of like does a tree shaking and removes unused code from the JavaScript output. There are Kotlin wrappers for the HTML parts, and the Ktor client is really nice to use, and the serialization library is nice to use. But a lot of the DOM API doesn't have these nice Kotlin wrappers. And if you're using an existing JavaScript library, you probably want to add your own Kotlin wrappers on top of that to make everything nicer to work with. So there are some more Kotlin wrappers needed. The build system is almost completely undocumented at the moment, very much because they replaced the old build system for KotlinJS with something new just very recently. But if you are on the Kotlin Lang Slack, or if you go to their support page, you can usually find help there. Something I'm missing is like splitting up the code properly in multiple parts, so that service worker doesn't become so awkward to work with. You can do it today with a single file, but yeah, this is something I'm waiting for. But overall, everything looks really, really promising. And I think it will be a nice alternative for those of us who prefer Kotlin over TypeScript, or where you have a large project where everything else is Kotlin. So it looks very promising. We're almost there, and for a lot of the cases, it already works fine. Now I'm going to do another recommendation also today at 1 o'clock. There is a talk about the state of KotlinJS. I think that's more going to focus on the actual build system and how to use that one and set up your project. It's a little bit different focus from mine. There is also another talk tomorrow, more full stack talk about where they talk about Kotlin JS. So if you're more interested, go see those. Now I'm going to do as my cat. I'm going to chill out for the rest of the day. So thank you very much for having me. We went really fast, so we have time for questions. But thank you, and remember to vote. Questions?
Thank you for your speech. I have a question. Did you try to use Webpack loaders for Kotlin?
Sorry, the what?
Webpack build system.
Buck build system?
Yes.
Webpack. Yeah, oh, sorry. Yes, did I try to use Webpack? So the new Kotlin build system, and I think Sebastian is going to talk about that at 1 o'clock, it actually wraps Webpack, and you can configure Webpack there like you do normally. There are some configuration options in the Gradle script. I don't think I have, and let's see if I can, yeah, here. So it's basically after the browser there, you can add a Webpack option and you can put some parameters there. It doesn't have the complete Webpack support. So if you want to do more, you need to add your own Webpack configuration in a folder in your project with the proper JSON stuff. Yeah.
Okay, thank you.
Thank you for the presentations. And I just heard that the Boolean types can be replaced with the dynamic keywords. I would like to know the difference between dynamics or the type any. Can we use the any type to replacement as a Boolean type?
If there is a replacement in union type in Kotlin, or?
I mean, in Kotlin mentioned that we can use the dynamic, the keyword dynamics.
Dynamic, yes.
Yes. But just curious, what is the difference between dynamic and the type any? In Kotlin, we have the any.
Oh, yeah. So any is actually you actually return an object. You could use any instead of dynamic, but any is always also an object there, and it might not always map to what you want to do. So you can always map it to any, yes. But if you have like function calls or stuff like that, or more complex JavaScript stuff that's not easily mappable, you use dynamic instead. So any would probably be the fallback before you use dynamic.
I see. Thank you very much.
More questions?
Since you said it depends where things are about Kotlin JS, for React, where does that depend goes?
Yeah, so what's the state of React? So I think that currently, because they changed the build system to the new JavaScript plugin, things are a little bit more shaky on all the existing libraries, so they are not, so it kind of took a step back there. It works fine. I haven't noticed any big issues. The problem I have noticed is importing third-party JavaScript libraries or React components and stuff like that. That has turned out to be not perfect. Yeah.
Thanks.
On the same topic, is a place where we can look for supported third-party libraries supporting Kotlin, or a central place we can look for?
Yeah. So are there any references to? So yes and no. You have the regular KotlinLang.org, and you can find some things there. But again, as the new build system is very much not documented, updated and documented at the moment, and the Kotlin JS stuff on the KotlinLang website points to the old one. So it's kind of like, so unfortunately, no, there is no good resource that I can point you to for like up-to-date stuff, but I expect that to happen very soon because people are actually requesting the Kotlin JS things much, much more now.
Thanks.
Hi, thank you for the talk. You mentioned that output size can be very big, and you also talked a little bit about that code elimination in the end. Have you tried this in production, and could you talk a little bit more about like how big it can be and how effective that code elimination is at the moment?
Yeah, it's hard to give a number, and no, I only used it on like my private small projects mostly, so I haven't done like a large production scale thing yet. One big problem with the output can be if you add coroutines. That significantly increases the JavaScript output. So that one, so if you exclude that one, you're usually fine. There's no problem. And I think that the dead code elimination for coroutines is probably something they need to work on more. Yeah.
Thank you.
Hi, thanks for the talk. Question is, you mentioned, like you showed us already how we can generate Kotlin definitions from TypeScript definitions. Is there a way to go backwards? Can we generate DTSs from
I see what you mean.
code?
Yeah. So if you would like to publish, you write your JavaScript library in Kotlin, you want to publish it. Yes.
Right.
I didn't include that one at all here. I think Sebastian is going to talk about that at his talk. But yes, you can definitely publish npm packages using Kotlin.js.
With TypeScript definitions.
Pass. I don't know. I haven't tried it, but I don't know. I actually don't think so. I don't think that's there. So. Unfortunately not.
All right, thanks.
There's one more here. I like that you have a lot of questions. Usually that's not the thing.
As a follow-up to what he just asked, in the keynote today when he talked about Ducat, that was the thing I was hoping he would talk about, because we want to go back and forth between both languages. But in the keynote, at least in the slide, the arrow pointed both ways. That they seem to want to make those equivalent to each other and go back and forth. I mean, there's no reason that they shouldn't be able to do that.
I know. I guess so. I mean, it's the pend statement there.
Yeah. Fingers crossed.
Yeah. Definitely.
Hello, thanks for the talk. Did you also look into using Kotlin.js for pure node development and maybe backend like lambdas on the Amazon cloud or Firebase functions?
Yes, if I've used Kotlin for like AVS Lambda or those things. No, I haven't. And since most of those backend stuffs also support Kotlin, I have a little bit. I haven't really seen the point of doing from Kotlin to JavaScript when I could actually just run Kotlin. But they should support it. They have, instead of using browser there, you use Node. Oh, yeah, I don't remember exactly, but that part is still is possible. Yeah.
Can you say something about your experience debugging this code when it's running and you're working with it?
Yeah, so debugging the code is, so what the build system does, it outputs a source map that points to your Kotlin code. So when you open up the source code and you put a breakpoint or something, you actually can see your Kotlin code and debug that one in the Chrome debugger or whatever debugging tool works. So it works, yes.
But in the keynote, they showed live updates. Have you any experience with that?
No. The live update, yeah. So they use Webpack for that. So basically, they continuously run the compiler. The Kotlin compiler for JavaScript has this parameter where it continuously compiles any changes you do. So I think they just pass that one in into Webpack. That works today already.
Okay, thanks.
Cool. I think we're running out. Do we have one more question or? Okay, one more question.
Yes, since we're already talking about debugging, how do you do testing? Can you use JavaScript testing frameworks, or do you need to use Kotlin test?
Yeah, so there are support for the JavaScript testing frameworks, but you should also be able to use like regular JUnit, because if you just have your Kotlin code, I used that approach, so I didn't use a JavaScript framework for testing. But I guess there is a point of doing that as well. But yeah,
thanks.
Cool. Okay, I think that's it. Thank you very much for coming, and thanks for all the questions. If you have anything more wondering, just come find me. I'll be around both days.
Okay. So I see that a lot more people is coming. Let's wait for 1 minute more, and I will start. Okay. So, yep, let's start. My name is Vladislav Tankov. I'm the software developer at JetBrains. I'm working on a few different projects. One of them is Kotless, Kotlin Serverless framework. I expect that some of you have some expectations, and I think I should reveal that Kotless is not used in a new product that will be announced today, but still it is kind of a cool technology, and we'll see if it can be used there. I expect that most of you know what Kotlin is. At least we are on a KotlinConf conference, which is a conference for Kotlin, a lot of Kotlin words there. But I'm not sure that all of you know what serverless is. So who ever did anything with serverless infrastructures? Okay, a lot of people know what serverless is. But still, I will remind about it a little bit. What is serverless, when it should be used, how it is constructed. It is kind of a naive definition of serverless for those who never heard about it and for some reason is on this talk. So as we know from Wikipedia, serverless is a cloud computing execution model in which the cloud provider runs the server and dynamically manages the allocation of matching resources. And Wikipedia never lies, so it is true. Cloud computing execution model that manages the allocation of machine resources. In general, it means that in serverless infrastructures, your application that is deployed to some managed runtime is managed for you. It is scaled up automatically, it is scaled down automatically. In case of fault, it is respinned automatically, and so on. When we talk about serverless, we need to understand the building approach. And it is pretty simple. There are 3 simple steps of building a serverless application, also very naive. First of all, we take small elements, stateless functions, and by stateless, I mean that they have no state, global state, static variables, or anything else. You have only parameters that are arguments of function, you do something with them, and returning some value. This is kind of a stateless function. Then we take events and compose with those events our stateless functions into an application. Events are pretty known, pretty popular programming concept. You may see them everywhere in mobile frameworks, in UI frameworks, anywhere. So I think everyone understands what is this. In the end, we take our function-based event-driven application, a lot of buzzwords, and deploy it to cloud runtime. In general, it may be not only cloud runtime, but also any managed runtime. So you can deploy your application, serverless application, into AWS, but you can also deploy it to some servers that DevOps of your team are managing for you. And if they have some automation to scale up and scale down your application, your functions, and perform all the event dispatching inside this application, it is kind of a serverless too. So we might take a look at this pretty complex example of a serverless application. To understand it better, we have an HTTP application that responds from REST API. We have two users. Do you see a red side? I hope. Yes? Okay. We have a user that requests /a, and the REST API of our cloud provider handles it and transforms an HTTP request into an event of HTTP request to /a and dispatches it to stateless function or Lambda. In reality, AWS Lambdas, it is kind of a trademark, but in general, everyone is using stateless functions and Lambdas as equivalent terms. So it dispatches /a handle request to Lambda, and this Lambda may use some other cloud resources, kind of a DBs, DynamoDB in case of AWS. It may asynchronously call other Lambdas and so on. Our user that request /b also goes through the REST API. It translates the HTTP request into HTTP event that will be handled by Lambda that handles /b. It will synchronously call other Lambda and will return some response to REST API. And back, REST API will kind of transfer an HTTP event of a response into a real response to the user. And the user is waiting for the response of the request on REST API. As we see, in general, you can build really complex serverless applications. But the idea is pretty simple. And when we say that idea is pretty simple, we expect that implementation will be also really simple. Let's take a look at this example. We have here a function that has a get annotation, and if you ever did any work with JAX-RS-like annotation, you ever wrote some Spring applications, you may expect that this function will produce a get handler on /hello world that will handle get methods and returns hello world. In general, we have a lack of context here. We don't know what the headers are, what is the MIME type, but we can assume some reasonable defaults. For example, that MIME type would be any time is plain text, and the headers are content length, and that's all. But right now, people deploy such functions with the approach of infrastructure as code. And how much of you people have ever heard about infrastructure as code approach? Well, also a lot of people. So, as a little reminder, infrastructure as code is the process of managing and provisioning computer data centers through machine-readable definition files. In general, it means that you are writing a definition of your infrastructure in some file. For example, with the HashiCorp configuration language. Anyone heard about Terraform? Yep, great, because the rest of the talk would be a little bit about Terraform too. So you are writing a definition of your infrastructure with some configuration language, and then you are asking infrastructure as code tool to apply this infrastructure to some cloud provider, or any other thing, but in our case, cloud provider. And it will create the resources that are defined in your configuration. And the infrastructure as code idea, approach is pretty cool. But with infrastructure as code, the building of serverless applications is not that simple as idea is. There are a lot of problems, and one of them is tons of configurations that you need to create a really simple serverless application. Here you can see a part of the definition of the function we've seen above. For the function that I've chosen as an example, you will need more than 100 lines. And the function is 5 lines. And you need more than 100 lines. And it is not really a trivial code. You need to pretty good understand what is going on and what you are trying to create. And in case of hello world, you just add in annotation, write in return hello world, and everything should work. And in case of Spring, it will work. In case of serverless application, you need to know also about HashiCorp configuration language, Terraform, CloudFormation, nothing works, what the hell, and so on. So 100 lines for this function. If you want to create a dynamic, partly static site that is serverless, well, it is a real pain. And you will need more than 1,000 lines for a simple site. And this is not the worst part, since if you need to create an infrastructure definition, infrastructure as code tool, you need to know the exact language of this infrastructure as code tool. And the problem is that each infrastructure as code tool has its own language, its own abstractions, a lot of its own resources, and so on and so forth. So in case of Terraform, they have more than 660 providers. Each provider has its own resources, own data, and so on. So you will need to know a lot about cloud provider, where you are trying to apply your infrastructure, and about Terraform, to understand how you need to apply this infrastructure. Let's take a look back at our example and ask the question: if could it be simpler? Can we create an approach that will kind of understand what we want to create, what infrastructure we want to create, and do it for us? So here's a pretty simple example, the same example. We understand here that we need a REST API, and we need one handler for this REST API, and this handler should respond on GET, and this handler have path/hello world. We don't know headers. That's all. But everything else we know. And in case of infrastructure as code approach, we need to duplicate all this knowledge in infrastructure as code file. So in a lot of cases, not only in JAX-REST-like annotations, but in a lot of more cases, I will discuss it a little bit later, infrastructure can be deduced from code. For example, in our case, we can deduce that we need the REST API and the exact handler. And when infrastructure can be deduced from code, infrastructure should be deduced from code. You know, the life of the developer is already pretty complicated, and we don't want to make it more complex. We need to make it simpler. So I'm introducing a term of infrastructure in code, which is application framework and deployment tool that writes with which you are writing the code with the help of a library that is provided by infrastructure in code tool. You know the difference as in. Were nicely done, I think. So you are writing the code with the help of the framework that is provided by infrastructure in code tool. In case of Kotlin, it is kind of a library, jar library that you are using. Then during the deployment, infrastructure in code tool introspects the code and creates actual infrastructure for this code and deploys the application into this infrastructure. Moreover, during the runtime, we know that in case of AWS clouds, other clouds, you need to have your own interfaces to handle the events from the cloud. So infrastructure in code tool provides the handlers and translate the events from the cloud into events inside the framework that it provides to the end user. So this is actually what is Kotless about. Kotless is infrastructure as code tool, and the code we've seen a few times already is an actual Kotless code. This is everything you will need to deploy a REST API into AWS. And it will work as we would expect from Spring application or any other application. So Kotless is infrastructure in code tool for Kotlin. It has its own Kotless domain-specific language for HTTP events. It is a set of annotations that you are using like JAX-REST-like annotations. It has its own Gradle plugin for deployment of the whole infrastructure. It uses Terraform under the hood, and everyone who knows what Terraform is saying, hey, it's a major tool, I like it, but I need to write a lot of code here, and here I'm not writing any code, but it still uses Terraform. In the end, it supports now only AWS, and we know that AWS is kind of the biggest cloud right now, but we are aiming to support also Azure, Google Cloud Platform, some open source alternatives, and so on. I will show you a brief demo of Kotless application, and I hope it will not fail. So we have a shot.kotless.io. I've even bought a domain with IO, you know, real hipster. So we have a shot.kotless.io. It is a normal application. We can kind of refresh it. It will work nice. We can shorten a link. It is a URL shortener. and your shortener shortens the links. And it will even work, I hope. It works. And it's not providing a recursion. It's not a recursion. Let's take a look at the code. We will need a presentation mode here. So we have Gradle. And some of you may not like Gradle, but I like Gradle, so we have a Gradle. We have a Kotlin JVM version 1.3.15, and we're applying a plugin named io.kotless with version 0.1.2. Also here is the io and io.kotless, like io-cater, but kotless. We have also here an implementation dependency that is dependency to kotless lang, a set of annotations. Let's take a look at the definition of the application. We have here get annotation with path slash, and it just returns HTML. Let's take a look. This is the exact this HTML. Now I will need to exit presentation mode, I think, to enable Gradle tool. Let's change a little bit our application and redeploy it. Shortless at KotlinConf. We have a few tasks in Gradle named Kotless. One of them is deploy, and we want to deploy, so we are deploying it. And a little bit of magic will happen here if Wi-Fi is stable, I hope. Kotless will automatically download Terraform files. Then it will perform a generation of Terraform, and we can take a look at the Terraform that was generated. It is more than 500 lines for short.kotless.io. It is generated automatically, and the end user should not ever take a look here. But in case you are DevOps, you know that Terraform is a good thing and you want to use it. And since we have a generate task that generates Terraform, you may reuse it. Reuse Kotless for deploying of parts of your infrastructure with generation of Terraform. Now let's take a look at the deployment procedure. It is destroying and respinning API gateway and so on. We have a lot of resources here. And I hope I've changed the right thing. It respins the application right now from the Lambda, and we see shortlist at KotlinConf. Nice. How does it work? We have a few annotations that defines exact handlers. Get annotation for root main page. A few get annotations that defines a redirect URL. It is a get method that will create redirect, will return a redirect. Oh, no. Okay, shorten is a get method that will perform real shortening. It will go to DynamoDB, will create an alias, and will return the alias. Since I'm not the best guy, I'm using get, not post. And you know it should be post. Yeah. One second. Back to the presentation mode. Forgot about it. So now you see, right? We have get /shorten, and it generates /shorten URL that will actually shorten links. And each call to /shorten will be dispatched to this function. And as you see here, we have an argument, and this argument will be automatically deserialized by Kotless. Right now, we are not supporting generation of schemes for API gateway to automatically validate what URLs are, but we may support it in the future. We have a redirect URL that will perform actual redirection, and all these handlers will be used by API gateway and will be created automatically, as well as the API gateway resources for them, REST API resources. Also, we have such thing as static get annotation. You know, when you have static resources, it is a waste of resource to serve them using lambdas. Since you have only one file and you need to return it to the user, it never changes, and so on. So Kotless solves this thing, creating actual static resources that will be connected to REST API. In case of AWS, we are using S3 bucket objects that will be connected to API gateway, and API gateway will be serving bucket objects right from the S3. So this is pretty much everything I want to say right now about Kotless. Let's get back to the presentation. So the question is, how does it work? Here is the pipeline of Kotless. we have a Kotless domain-specific language. It is annotations you've seen. Using Kotless parser, it is a plugin to compiler that's used by a Gradle plugin. We are parsing the domain-specific language and understand what is the actual infrastructure that is needed for this application. And you may see here that, in general, this approach is not kind of limited only by serverless applications. With the same approach, we can understand, for example, what is the Docker file for our application or anything else. Then we are generating Kotless scheme. It is a cloud-agnostic scheme that is defining in a common terms the serverless application, saying that is a stateless function, that is the handler, that is the REST API resource, and so on. And then scheme is used by Kotless engine that generates Terraform. And the Terraform is applying Terraform files into AWS, and everything is good. What this pipeline gives us? First of all, we are using cloud-agnostic scheme, and it means that in general, we can generate not only AWS deployments, but Azure deployments, Google Cloud Platform deployments, IBM deployments, or anything else. Secondly, we have an abstraction of deployment. As you may see, we are using only scheme during the generation, so we can generate not only Terraform code, but also CloudFormation code, or Pulumi code, or anything else, any else infrastructure as code. Even we can generate serverless.com code, if you have a question about it, but it's kind of our nature enemy, so we would not do it. After it, we are generating Terraform and applying it. In the end, we have a pretty interesting thing. We have an abstraction of domain-specific language. As you may see, we are using only scheme during the generation of infrastructure. And the only thing that knows how is defined actual application is Kotless parser. And in general, it means that we can replace parser with any other parser and kind of parse some other domain-specific languages. So emerges the question, why not support existing framework? Why should we reinvent things and adding new JAX REST-like annotations? And we do support existing framework, we support Cater. So we can generate serverless Cater deployments. And I hope some of you know what Cater is. Okay. Not as much as Terraform, but anything. So we have pretty much the same build Gradle KTS. I hope everyone is using Kotlin script in Gradle. And today, Andrei showed that autocompletion now works a lot faster, so it is not pain anymore, as it was. We are redefining the type of DSL, saying that we will parse Cater files, and we are using Cater-lang. And this is an implementation of Cater engine that is used by Kotless and that is optimized for serverless deployments. I know that a lot of people right now, some people right now, are deploying actual Cater server into serverless, kind of pruning things out of it and trying to make it work in Lambdas. So we are implementing our own engine that is lightweight and that will do only the work that is needed during the serverless runtime. We have as an entry point a Kotless class, Kotless abstract class or interface, I don't remember. So we have as an entry point Kotless class, and it has exactly one entry point function, funPrepare, that returns you a simple Cater application. On this application, you can set up the get handlers, post handlers with the Cater DSL, and everything will work. We are using here static feature of Cater that will generate static resources, and we are using dynamic handlers with get, post, and so on. So what happens after it is that Kotless is introspecting application, finds the methods of Cater that are known by him, and generates actual infrastructure. And as I said, this approach can be kind of generalized, and we can support not only Cater in this way, but also Spring or any other framework. We need to just kind of change a little bit parser, say to him that now you are parsing not annotations but get methods or anything else, and it will generate infrastructure for Kata or Spring or any other thing. Yep, back to the presentation. Oh, I didn't show you, but Kata application is also deployed, so I'm not lying. You can see it at kata.short.kotless.io. I have a good imagination. And it should also work. And we have here powered by Kotless and Kata. So, let's get back. The idea of creating serverless infrastructures for existing frameworks brings us the idea of few domain-specific languages that can be used during the parsing. And it brings us to the idea of seamless serverless. Also, I'm introducing kind of this term. In this concept, you are writing the code with any web framework you like. But if you are using Kotless, you are writing it with Kata, and it means that you like Kata, at least right now. After it, you can run it locally, since you have actual Kata deployment, we can actual Kata code, we can replace the engine with the engine that can be used locally, and you can debug your application locally, run it locally, even have a hosted solution, standalone. Then you are deploying it with a seamless serverless tool like Kotless. It introspects the code of your framework, understands what is the serverless infrastructure for it, and generates deployment and deploys it. In the end, you have a serverless application in the cloud, and you can even have a standalone application in-house. So it may be interesting and well, important for those who are willing to have not only cloud deployment for their application, but also a standalone application for guys that kind of from Army or from FBI, and they want everything not in cloud, but everything at their office. You can say that, okay, guys, we have a standalone application, and the serverless application works exactly the same way. Yep, it is interesting, but let's go even further. We've discussed an HTTP REST APIs. We've discussed, well, pretty much only it. But there exists a lot more things about serverless. First of all, we all know that serverless is used for handling an events. And if you are using serverless, you may want to schedule some job, use cron expressions to have some jobs scheduled, and so on. You will also need a permissions granting. Since Kotless generates fully infrastructure for your application, you will not be able to say that this exact serverless function should have an access to this exact DynamoDB table. So we need to provide you with an ability to say that some objects inside your code are requiring some permissions. In general, this is not only the things that, this is not the whole thing that code may fully define. In general, code may fully define API interaction. We've seen it already. It is get, post, and so on. It can define events handling, not only scheduled, but custom events from AWS, Azure, or any other thing. It can define permission requirements with annotations, or in some cases, we can kind of deduce things and understand that you are using DynamoDB client, and during the compile time, we can understand what is the table used here and what are the functions that is called, and generate permissions for it. In the end, that is not yet implemented. We may understand that you are using shared structures. It means that if you have, for example, two scheduled functions, one of them is popping values from the queue, and other is pushing values to the queue, we understand that your functions are not really stateless, and they will not work in the way you expect. So in this way, in this case, you will have one function, since it's stateless, it will be popping from empty queue, and other will be pushing to queue that already has a lot of items. So we understand that you want to have a shared structure, and we can kind of replace in code the calls to this queue with calls to DynamoDB table, generate this DynamoDB table, and make it work like a queue. In the end, some calls of functions, not coroutines, but still, for example, you want to call asynchronously some function, and we understand that if you are deploying it as a serverless application, you would love if we would capture the context of this asynchronous function, understand that you will use it inside its body, and make it a separate serverless function that will be asynchronously called and will be working, and your serverless function that has been calling it asynchronously will return the value. So let's take a look at some Kotlin advanced features. Not all of them are implemented right now, but some are. It is also in Kotless shortener. First of all, we have permissions granting. It is a URL storage object that is used to push some data into DynamoDB table and pop some data from the DynamoDB table. I say that this object, any access to this object will require read and write permissions for table short -URL -table. And each stateless function is inside my application, if it will access this object, will be granted with permissions to read and write to this table. Also, it can be kind of applied to some functions, and you can granularly separate permissions and say this function is only reading from the table and this function is only writing to the table. And if your stateless function is only reading from the table, it will be granted only with permissions to read from the table. Also, we have schedule functions. This function is used inside shortless URL shortener to clean up the storage of URLs. It will clean up all the URLs shortened each 3 hours, since it is example, it is okay. And we have here scheduled annotations that defines a behavior of running each hour for this handler. And we can have here any arguments, since we don't know what the arguments from the context. Yep, and one interesting detail, it is extensions.cf. Kotless right now is not able to express fully what Terraform is providing you. For example, we cannot create, I don't know, Cognito, we cannot create DynamoDB tables, and we are not aiming to replace Terraform or CloudFormation or any other thing. We are trying to make deployment of serverless applications simpler. And if you will need to create DynamoDB tables with some DSL, it may be even more complicated tasks than just use Terraform. So Kotlin provides you with the ability to define that some Terraform files are defined in your project and should be used during the deployment also. So with this, I'm creating DynamoDB table for URLs with extension and defines in build Gradle.ks that is the extension to generate a Terraform file. Yep. Let's get back to the presentation. So I've kind of defined all the aspects of Kotlin right now. What's next? We are working hard on different things. First of all, it is supporting of other clouds. We are aiming to support Azure. We are aiming to support Google Cloud Platform. But it is really connected to the second point, supporting of Kotlin multi-platform projects. You know that Kotlin provides you with different targets, different runtimes. You may generate JavaScript code, you may generate native code, you may generate Kotlin code, JVM code. And depending on the tasks, you may need and want to use different targets. So we want to provide our users with possibility to generate even JavaScript lambdas from Kotlin, native lambdas from Kotlin, and JVM lambdas from Kotlin, so they can choose the runtime. And it means that we can support, for example, Google Cloud Platform, since Google Cloud Platform, as far as I remember right now, supports JVM only in beta. And JavaScript is not in beta, so if we would have Kotlin multi-platform projects, we could support JavaScript or Google Cloud Platform generating JavaScript. We aim to support extended event handling of custom events in AWS or in any other platform, and much more. The work on performance, the work on other things. For example, we've been thinking about performance from the start, so we have auto-warming of lambdas, our lambdas optimized by size, and so on. This is practically all I wanted to say about Kotlin and its state right now. I hope that you will give Kotlin a try. Here's the QR code that navigates you to GitHub repository, and here's my email. You may ask me with it or right now. I hope it was interesting. Thank you. all the questions, if you have any.
So, am I right that by default the target for AWS Lambda is JVM with Kotless?
Right now, yes. Yes. We are aiming to solve the problem with performance of JVM, making auto-warm of lambdas. So it works pretty nice, and for sites, for serverless sites, it works like, I don't know, JavaScript, without a cold start almost. Yep. Any other questions?
How do you configure your resources? Because you're going to have a test environment and a production environment, and they might use different buckets, different things. How does that work?
Okay, yep. Inside the build Gradle KTS, you can specify, first of all, prefix for the whole resources to make sure that they not clash inside your account. It's called prefix. In case of shortener, I don't have production shortener and staging shortener, so I have only prefix short, and it guarantees that your resources will not clash. Also, here's the configuration of a bucket that will be used by Kotless, a working directory, but it's for generation, and so on. The profile region. So you are defining everything of it inside the Gradle. We have reasonable defaults. You do not need to specify prefix if you don't need it, but when you have staging and production environments, you need it, and you can specify it right here. Since it is a Gradle, you can kind of get, for example, from environment parameters, from SSM, from console, from anywhere, prefix, and use it. During continuous integration, continuous deployment.
Hi, you have DynamoDB annotation for giving read-write access. Are there many other
yep, we have
you can grant access to? And if not, is there a way to use drop down to Terraform whenever we need to? Because there's a lot of resources to cover.
Yeah, I see. We have more annotations for SSM, also for S3 bucket, and I'm adding annotation during the new releases. And if there is an issue for creating annotation to provide ability to grant permissions to some resource, I will add it. Also, you may have noticed that we don't have a granular permissions. We have permissions that kind of state you have a read access or write access. And it is done for a reason. We wanted to make it simpler, so you cannot provide your function with an access only to list DynamoDB table. It will be provided with the whole read-only access to the DynamoDB table. But for our use case, we want to make it simpler for user to use it, to use serverless applications. It is okay. And we don't want to change it. So I'm not sure that we will be providing annotations that provide you with ability to create granular permissions.
Sorry, just and then if there is no annotation support, is it possible to just go into the extensions file? Is there any way to do it from there if needed?
Yeah, you can create IAM role, add some IAM policies, and it will everything work. Yep. Any other questions?
So you have this special Gradle plugin and a Kotlin plugin, but in your build Gradle file there is a third plugin you didn't mention. So what purpose
okay,
does it serve?
It's kind of a mine plugin.
Yeah, it has interesting name.
You mean Kosogor plugin?
Yeah.
Okay, it's a funny joke for us.
Is it necessary just?
No, it's not necessary. It is kind of configuring your project to exclude directories. You see that build Gradle is excluded automatically and so on. It configures IDEA to work nicely with Gradle with the more reasonable defaults by from my point of view.
Okay, thanks.
Hi. If I have a traditional and non-serverless application, would it make sense to just describe the infrastructure with this? So I know I want a database, I want my application as jar somewhere.
Yeah, I see. It depends on the use case. Serverless gives you a possibility to have fault-tolerant application that can work under the high load. The maximum of working in parallel lambdas for AWS is 1,000 lambdas, and each lambda is working about 50 milliseconds. Yep, so it is more than, I think, yeah, 20,000 parallel requests per second. So in case you have a high load, you can use serverless. It's true. Also, you can use it in case you have a really low load. Under the middle load, it possibly makes no sense, since you don't need such parallelizing possibilities, and you have a lot of requests. You can deploy it only. You can deploy it in a default way on instances. But in general, yeah, you need to use serverless to cut expenses, and you need to use serverless under the high load.
Thanks.
Yep. Other questions? Well, I think that's all. You can find me on a venue. I'll be somewhere near the JetBrains booth if you have any other questions. Thank you.
So, hey everyone, my name is Tom Hanley. It's an absolute pleasure to be here. Great to see such a packed house for to hear about coroutines. So I'm going to be talking to you today about a coroutines case study. So how I used them on this project over the last year to clean up an async API. So you all know callback hell. It's called callback hell for a reason. Async code can get really messy really quickly, and there's lots of ways to avoid this in your design. But sometimes you have to live with this async API. Maybe it's too difficult to rip out and rewrite, or maybe it's provided by a third party. But what you can do in this case is write a wrapper or extension on top of it using coroutines to bring it into the coroutines world and make it nice and easy to use. So I think Kotlin coroutines are a fantastic way to clean up async APIs. So they can make your async code as easy to read and understand as sequential code, but give you all the benefits of non-blocking code. So yeah, a bit about myself first. So my name is Tom Hanley. I'm a senior software engineer at Toast in Ireland. I'm also organizer of the Dublin Kotlin user group and a huge fan of Kotlin. So yeah, just a quick primer on coroutines. So I guess quick survey first of all. Who here has used coroutines before? Okay, it's a good number. Who here has them in production? That's a very good number also. Okay, great. Okay, so I'll do a quick primer just to kind of refresh your memory. So why coroutines? So essentially threads are expensive. They can occupy 1 to 2 megabytes. And you need to use thread pools to manage them to use your resources carefully. So coroutines, they can be thought of as lightweight threads. They kind of look and feel like lightweight threads. But what they are actually is state machine objects. So they have the data for each state, the index of the current state, and the ability to wait patiently. So when you think of them as objects, it kind of makes sense how they're so cheap to create. And then you can distribute these objects to run on whatever thread pool you want really easily. And there's two main ways to create coroutines, so launch and async. So launch is for fire and forget coroutines where you don't want to return value. And async is for a coroutine that computes a result and you want to get a result back. So these behave a little bit differently in terms of error handling, which I'll get into in a bit. Okay, so the case study. So I'm going to tell you a bit about Toast and the project I was working on, the problem we were faced with, and kind of run through an example of what the code might look like without coroutines and how we use coroutines to solve the problem. So Toast, we're a restaurant software company. So our core products are cloud-based point of sales and credit card processing. And all of our in-restaurant technology runs on Android tablets. We've web interfaces for managing restaurant configuration, reporting, and consumer-facing websites and apps for online ordering and guest feedback, those kind of things. And also integrations with technology partners like Deliveroo, Just Eat. And you can see at the bottom there some of the tablets we'd have in a restaurant. So we can have we'll have multiple tablets running in a restaurant. So one in the kitchen showing the orders coming in, multiple ones in the front of house with servers putting in orders, taking payments. And we also have a takeout app, so like an order ahead sort of app. So then, yeah, the sales pitch slide. So we have a 250-person R&D team, tens of thousands of customers in the US. We're processing billions in payments every year. July 2013, we got our first live customer. And last April, we got 250 million in Series E funding, valuing the company at 2.7 billion. Less than 10% of the US point of sales market share so far, so lots more growth to come. So if you're interested in some of the stuff you hear today and you want to hear more about Toast, do get in touch. So, end of the sales pitch. So the project was integrating a new credit card reader into the application. So it's a USB-connected credit card reader, designed and manufactured by an external hardware company who provided us with an Android SDK. And the project was to integrate it into our Android application. So yeah, there's multiple integration points. So there's like a bunch of different screens in the app where you can pay. It kind of just needs to work in the background. The reader turns on without you explicitly telling it to. So yeah, it just needs to work on a couple of different screens, run in the background. So be very efficient with its use of resources. So coroutines were a really good fit as well for that. And yeah, of course, all the calls to the reader need to be asynchronous. They're I/O calls. They're going over a USB connection. We don't want to be blocking, waiting for any response. So the API, what does this look like, the one that we were given with the hardware? So you can see here, so there's two main classes to interact with the card reader, and on the left there is the physical card reader. So one, we have the controller, so this is to send commands to the reader. These are all void methods, so you can't get any data back. To get the data back, you have to implement this listener interface, which you pass in. And this will asynchronously return all information and errors from controller commands, and yeah, this is implemented by us. So this might sound okay that it's ticking the box for being asynchronous, but in reality it's very difficult to use cleanly and correctly. So yeah, we're going to take a look at a small section of the API to illustrate this. So the function to get the device info. So this will give you some data about the card reader, so like the serial number, firmware version, battery level, that kind of information. So if we take a look at the cross-section of the API for that, so we have our controller interface with a get device info method. It's a void method, it doesn't return anything. And then we have our listener interface that we implement, so whenever the card reader returns the device info, it'll call this method, or if it returns an error, it'll call the onError method. So what might the implementation of this listener look like? So if we take a look at a naive implementation first of all, so here we're implementing the listener interface, and whenever we get a device info in, we just save it to a field, and we expose this to the rest of our code with a public mutable nullable variable. And we do the same thing for when an error comes in. We just save this to a field. And then a function to get the device info. So what might this look like? So we have our function that's returning device info, which is nice. The function, it's a getter. It's nice to return something from a getter. So first of all, we need to call get device info on the original controller. This is a void method. It doesn't return anything. And then we need to go to the listener and start looking for the device info or the error. So we have our loop here, and we're sleeping until we get get one of these. Then if we get an error, we save it to a variable, null it out so this works the next time, and we throw the error. Or if we get a value, we do the same thing. So there's a lot of things here that are asking for trouble. So we're blocking the thread with that sleep, potentially getting into an infinite loop. If we don't get back one of these, and we're using shared mutable variables to communicate, which is tricky because to make this thread safe, you need a bunch of synchronization and knowledge of the JVM memory model. So I kind of said life would be so much easier if I had a nice coroutines interface like this, a suspend modifier on the function, so it's not blocking a thread. So this suspend modifier indicates that the function can suspend the execution of the coroutine and resume at a later time. So you can execute long-running operations without blocking the thread. So yeah, to achieve this, there's some syntactical sugar. So under the hood, what's happening is there's a hidden continuation parameter, which allows it to continue the execution of the rest of the program once this function returns. And yeah, there's a really good talk by Roman about this last year, going into detail on that. So yeah, we said this was the interface that I wanted to get to. So we said let's try and get there. Let's clean it up by writing a Kotlin coroutines extension on top of this API that we had. And yeah, extension or wrapper, or maybe wrapper would have been a better name. We went with extension. We were going to call it controller.ktx, but someone didn't like abbreviations. And then controller with a K was also another vetoed name, but extension is what we went for, so bear with me. So yeah, so some of the goals of the extension. I wanted a nice clean API where the result of the query is clearly returned by the function itself, also known as referential transparency. The caller of the function can control the asynchrony, so if the caller wants to wait until it's finished to do something else, then it can, or if it wants to run it asynchronously, it can. We're not blocking any thread. Easy to use and hard to misuse. And you can know that one call is completed before starting another, which is important with the card reader, because if you need to wait for, like say you start the connection, you need to wait for the connection to finish starting before you try and start a transaction. So yeah, this is the interface what we wanted to get to. So how might we implement this interface? So at a high level, what we want to what we want to do is, first of all, start listening for the event or the error, trigger the event, and return, wait until the event or error is returned. So in our naive implementation, we communicated from one thread to another using shared mutable nullable variables. So we're kind of asking for trouble there, but what can we do here? Because this is going to require some asynchrony and inter-thread communication. So what we can do here is take some advice from the Go handbook. So do not communicate by sharing memory. Instead, share memory by communicating. So how can we communicate across coroutines? So enter Kotlin channels, a really nice way to asynchronously communicate across coroutines. They're kind of exactly as they sound. Data goes in one end, comes out the other. And this is roughly like what our extension looked like. So when we get a result back from, or when we get an event back into the listener extension, then we just pop it onto a channel and the controller extension can deal with that however it wants, or suspend waiting for whatever it's interested in. So channels, conceptually very similar to a blocking queue, but the key difference is that instead of a blocking put and take operations, they have a suspending send and receive operation. They're an experimental feature in Kotlin 1.3, which can kind of scare some people off, but I think it doesn't mean that they're not ready for production. It's just they expect the API might change going forward. And the huge advantage that Kotlin has is that the creators of the language also create your IDE, so the migration paths are very smooth. So yeah, if we take a look at what that listener implementation might look like using channels. So again, we're implementing the listener interface. When we get a device info event back or object back, we pop it onto the device info channel, and this is a public channel. Whoever's interested can receive the events on this channel. And we do the same thing with the error channel. We pop the error onto the error channel. So then our controller extension implementation, so the method to get the device info. So what does that look like? So we have our suspend modifier, returns the device info, and we delegate to this method called trigger event and get result. We pass in 3 parameters. One is a lambda that triggers the event, and we have the event channel and the error channel that we also pass in. So the implementation of this then, so first of all, we want to start listening, which is this block here. And we need to do this asynchronously because we're not going to get the event until we trigger it. So we put this in an async block. And then we use this really nice coroutines feature called the select expression, which allows you to select from multiple channels and just say, it just means like, give me the first event that comes back. So really, really nice for this use case. So we say if we get an error back, we throw the error. If we get the event back, we return the error. And then we trigger the event by invoking the lambda that we pass in, and then we call await on the deferred event from that async block. So yeah, the select expression makes it possible to listen to multiple suspend functions simultaneously. So not just channels, you can use it for any suspend functions, and select the first result that becomes available. So the resulting API and it looks a bit like this. So we can. It looks like normal sequential blocking code, but we can tell from the suspend markers in the gutter on the left that these are suspend functions. So we can check if the card reader is connected. We can get the device info. We can start the USB connection, and we can start the transaction all in non-blocking way. And yeah, also have the sequence diagram. So kind of from the application, so I don't know if you can read this, but on the application layer on the left, so all that it sees is the get device info and the return the device info as a suspend function. Then under the hood, the controller extension starts listening on the device info channel, then triggers the command to get the device info on the original controller. This goes to the physical card reader, which comes back, sends the event to the listener interface. We pop this onto the channel, and then the controller extension here it has called receive on this channel. So once it gets that event back, it will resume the execution of the coroutine and return the device info to the application. So yeah, that's the end of the case study part. I'm going to go into some of the key lessons learned along the way. So how to handle exceptions, debugging coroutines, which is some really good tools that have come out for debugging coroutines, which are especially useful if you don't know how to handle exceptions, as I didn't at the start of this. Some tips for keeping your coroutines testable and clean. And then finally, we came around to not throwing exceptions and moving away from this. So first of all, the coroutine exception handling. So yeah, just to talk a bit about structured concurrency. So this was introduced in Kotlin 1.3, and it kind of enforces a parent-child relationship on all your coroutines, so that if you cancel the parent, it'll cancel all of its children. It makes it easy to clean up your coroutines. So every coroutine is created in a coroutine scope, which enforces the parent-child relationship. And you should avoid using global scope, especially on Android, as you'll need to clean up your coroutines. And we have the parent-child relationship. So yeah, the parent-child relationship, as I said, ensures that canceling a parent cancels its children. But what I didn't realize at the start was, by default, this relationship is bidirectional. So if a child coroutine is cancelled, it'll propagate to the entire scope. So it'll cancel its children and its parents, and the same if it finishes exceptionally. Which will also on Android, if a coroutine finishes exceptionally for launch, it'll be treated as an uncaught exception and will crash your app. So if we take a look at the difference between launch and async error handling. So for launch, if we wanted to, so we launch a new coroutine, this throws an exception. If we put a try catch around it like this, that won't be caught. It'll be treated as an uncaught exception, and will kill the coroutine scope, and on Android it'll crash your app. So if you want to catch that, you need to put it inside the coroutines, inside the launch block. But it's a bit different for async. So say we have this function calculate number, does some work and returns an integer. We have our parent job and our coroutine scope to manage this coroutine scope. So the first number we want to calculate, this may throw an exception as it does here. So we have this in an async block. And we can, when an exception is thrown in an async block, it won't be bubbled up until you call await. So line 11 here, so that's when the exception will be thrown. So we can catch this fine, and our program is still running fine. We can default to a value of 0. Our value here is now at 0. But when we go to try and continue using that coroutine scope, so the coroutine scope is cancelled, so it will give us the same error as the first one that's thrown. So it can be kind of confusing if you handle this one up here, you catch it and you handle it, you have a default value, and then you try and use the scope again, but it's giving you the same exception or the previous exception. So there's some options to handle this a bit better. So solution one is to just make one change to this, so to use a supervisor job. So in the first line, so this job means that the cancellation is propagated only downwards. So a child being cancelled won't cancel its parent and its siblings. It'll just kind of it'll just cancel that one coroutine and its children. And another solution is to use a local coroutine scope block to group coroutines that are all or nothing. So what the coroutine scope block does is it inherits the parent coroutine scope context, or coroutine context, but it gets its own job for independent cancellation. So if we use the coroutine scope block here, so here we have our async and await inside the coroutine scope. That'll throw an exception, but it'll just cancel that coroutine scope. And then we can catch that below and continue on as normal. And then for the rest of our calculations, we have this in a separate coroutine scope block, so it won't be affected by the cancellation of the coroutine scope block above. So yeah, it's a good way to if you want to group coroutines that are all or nothing. So you're like, if any one of these throws an error, then the rest aren't valid. It's really good for that. So yeah, I guess to summarize the error handling tips. to use supervisor job instead of a job, and the cancellation is propagated only downwards. And to use local coroutine scope block to group coroutines that are all or nothing. So it inherits the parent context but gets its own job to be cancelled independently. So yeah, on to key lesson number 2, so debugging coroutines. As I said, really, really useful if you don't know how to handle exceptions. So yeah, first tip is to enable debug mode. So you can set this with a system property or -EA arg, so you should definitely do this for unit tests. And you can also set it programmatically based on your build type in Android. So what will this do? So first of all, it'll attach a unique name to every coroutine that's launched, and this will get appended to the thread name for debugging. Negligible overhead, so you should do this in production, or you can manually set it also at the individual coroutine level or at the scope level. And it'll also give you much better stack traces. So normally when an exception happens in a coroutine, you just get the stack trace for that coroutine. So if your coroutine is 1 line long, your stack trace is essentially 1 line long. So it can be not all that helpful. So this will piece together the full stack for all of your coroutines that are and child coroutines that are launched. There is a performance overhead, so it's not recommended for production, but you can enable one and not the other. Next really good debugging tool is the debug agent. So this was released last April. Unfortunately, after I had done most of this coding, but it's got some really powerful debug capabilities. So it's a JVM agent that keeps track of all the live coroutines, and it'll introspect and dump them similar to a thread dump command. And we'll also enhance stack traces to give you information on where the coroutine was created. So if we take a look at some example usage of that. So before we do some work, we install the debug probes. We launch some coroutines. Then we dump all the coroutines to the console. Or we can just pick one job and say, give me all the info on that job. So what does the output of that look like? So here we can have the coroutine name and the state that it's in. We have the current stack trace of the coroutine, as well as the coroutine creation stack trace. So it's a really useful information here. And also if we do the dump of a single job, so we can see this coroutine created this coroutine, and we can see the state of all of them. So yeah, really good for if you're trying to debug a deadlock and figure out what's going on. There's also a JUnit rule, so this will, if your test takes longer than a second, it'll dump all your coroutines to the console. And you can use it as a JVM agent, so it'll enable debug probes on application startup. So key lesson number 3, so some general tips around keeping your coroutines testable and clean. So first tip, which is not exclusive to coroutines at all, but it's to unit test everything. So it's especially important when you have a new API that you're trying to figure out and you want to validate that it works as you expect it works. So really good for catching wrong assumptions early on. And it's really easy to do with coroutines, so you wrap your test in a run blocking block, and then you can test your suspend functions as normal. Another really good tip is to only use launch and async when you really need concurrency. So let's look at an example to illustrate this. So say we have this function update data. It calls 3 suspend functions: get data, post data, update UI. So this will fail to compile. We'll get an error saying suspend function get data should only be called from a coroutine or another suspend function. And so the temptation here is to launch a new coroutine. Coroutines are super cheap to create. You can just launch as many as you want and not worry about them too much. But there is a drawback to this. So yeah, the temptation here is you launch a new coroutine on the I/O dispatchers for doing your network calls, and then you launch a new one on the main thread for updating the UI. So this will work, and it'll work fine. And you're like, I don't really care when this happens. Just it'll happen soon enough. But it does make this really hard to test, because when you want to call update data and then assert that your UI has been updated in a test, how do you know that the coroutines have finished running? So what you should do in this case is to prefer marking a function suspend to launching a new coroutine. So this will allows the caller of update data to control the context and the asynchrony and know when it's finished, and it makes your testing a lot easier. But you should control the context where needed using the with context block instead of a new coroutine. So, for our network calls, we use the IO dispatcher with context, and for updating the UI, we use the main dispatcher. So this will switch switch to a different dispatcher without creating a new coroutine, and just make it much easier to test. So then we have the question: what do we do with functions that launch long-running background coroutines? So say we have this function launch processing. It launches 2 coroutines, and we want to keep these running and run them in the background. What do we do here? So the convention in this case is to any function that returns before completing all of its launched coroutines should be an extension method on coroutine scope. So you're essentially passing in the coroutine scope to this function, and it allows you to cancel it when you want to and control how long they run for, which makes your testing a lot easier. Another option which does behave a bit differently is to make it a suspend function and use a coroutine scope block. But this won't keep running, or this won't return while these are still running. So the coroutine scope block will wait for all of its coroutines within it to finish before returning. And then key lesson number 4. So we said, after figuring out all that exception handling, we said actually let's not throw exceptions. So while they can make your calling code really clean, but when you actually have to catch and handle exceptions, things can get really messy. So yeah, that's why we moved away from throwing exceptions. So I guess first of all, why were we throwing exceptions? So when we were getting an error back from the card reader, we were wrapping it in an exception and throwing it. But yeah, not the best idea because USB connections are not 100% reliable, and hardware is not 100% reliable. So these are I/O calls that do fail sometimes. So we needed to catch these exceptions and recover. And when you have to do this, things get messy and awkward. So kind of did some reading on exception handling and kind of some of the alternatives out there. So what are some of the problems with error handling, with using exceptions for error handling? So your error handling code becomes more error prone. It's less explicit and easy to forget about your error handling cases, and it becomes a lot less predictable also. Much harder to understand the control flow. So your exception is thrown, it maybe gets caught here, it gets thrown up somewhere else. It's really easy to forget to catch them, especially with Kotlin, that you don't have checked exceptions. And it's also less functional. So if you want to keep your functions as pure as possible, throwing an exception can have some unintended side effects. If your function just returns a value for a given input, and those should always be the same, but you have this kind of wildcard that it might throw an exception, which makes it more difficult to test and easy to just not test. There is a performance overhead to throwing exceptions also and creating them, so there's that also. But I think the strongest argument I heard for not using exceptions was this one. So throwing and catching exceptions is comparable to using goto statements, which since long before I was born, this has been like the first thing that programmers have understood to not do. This is you have the power to do it, but you shouldn't do it. So yeah, this was kind of the conclusion we came to. Exceptions should only be used for fatal things that you can't recover from, and to avoid throwing and catching exceptions. So instead, return an object that encapsulates the success or failure outcome. So there's a couple of options here that we looked into. So first one we tried out was the Kotlin result object. So some really, really nice features, but unfortunately it's not ready to be used as a return value from a function because they want to be able to make some changes to it and keep it or maintain binary compatibility. There's arrows either object, which a lot of people really like, but I found the left and right convention a bit jarring in terms of readability. That you have the small cognitive load to remember that when you read left, that means error or that. So kind of wasn't a big fan of that either. Arrows try object, but you need to throw an exception for this, which I wanted to move away from completely. Another option we looked at was creating our own generic success or failure object, but this kind of felt like reinventing the wheel, and we were kind of running into some of the same issues with the Kotlin result object, that why they're kind of unsure about certain things, or this about what way to go on certain things. So another option then is to create our own domain-specific result objects using Kotlin sealed classes. So this is what we did in the end. So it leads to a bit more code and some very similar looking classes, but there's no sacrifice on readability, and it allows each result object to evolve independently. And error handling is easily enforced by the compiler when you're using when statements to handle these. And the error handling happens exactly where the error happens, not a couple of errors up where you don't have access to all the information you want. So it happens exactly at the error point. So we changed every controller command to return a generic result object. So we have our success and failure object with a result type and an error type. And we're not trying to be super generic with the error or trying to be all things to all return types. So just kind of for this specific use case, so it was easy to write. And then we can map this to domain-specific result object as needed. So for our device info result, we have success, failure, and timeout. But then, for other result types that want to evolve differently, like the start USB one, so we can have like already connected, success, failure, timeout, and handle each one of those differently as we need to. So some links on some of this info. So Keep 127, that's on the Kotlin result object, which has a really good write-up on the result object, its limitations, and some of the other alternatives that I mentioned before. There's a really good blog post by Philip Hauer on using sealed classes instead of exceptions in Kotlin, on how, why, and when you should use them. He mentioned that using them absolutely everywhere can be a bit arduous. We didn't run into this too much, I think, because we were just using them for I/O calls, which tend to fail. But yeah, I think you can go too far with this solution also. And there's a blog post that I published recently that covers a lot of the content in this talk. So Kotlin Coroutines case study, cleaning up an async API on Medium. So yeah, so that's it. So in summary, coroutines are awesome. Really, really nice to use. They make async programming easier, but not easy. There's still things to figure out. You still will have to figure out, or likely have to figure out deadlocks, and keep this cognitive load of what's happening in multiple places in your head. But yeah, it can make it a lot easier to use. So yeah, and also if you're in a toast restaurant in the US and you pay with contactless or Apple Pay or Google Pay, you can know that it's powered by coroutines and the content of this talk. So yeah, thank you very much. I hope you found that interesting and you enjoyed it. So thank you. Are there any questions?
What was the hands?
Can you hear me? Brilliant. So earlier on you spoke about the benefits of using coroutines in your code in terms of avoiding the cognitive load on a developer and follow the sequential style of programming and all that, which makes sense. But I was wondering if in the production environment you actually saw any performance benefits as well? So performance benefits between using callbacks previously and using coroutines explicitly. So I'm wondering if you would be able to quantify that for us.
So yeah, I'm not able to quantify it. Unfortunately, yeah, we didn't actually put the examples I put out there, not using coroutines. We didn't put these into production, but I guess the main focus was on it being easier to use, harder to misuse, safer, rather than being more performant.
Fair enough. Okay. Thank you.
Thank you.
Down here. I'm coming.
Hello, my name is Damian. Could you show the code handling errors, like with those sealed classes that you presented the idea with classes? Can you show how the code looks like?
Yeah, so I should have put that in. I was like, so yeah, I don't have that in the slides. But yeah, it's using when statements. It's full disclosure, it's not as clean as the this result. We are using when statements for each of the return values where we have logging. We're sending messages to the user. So it's not quite as clean as this but this was kind of early on as we evolved and started handling errors better. The code does get a bit more verbose, but it's very explicit, what you're doing on each error case. But yeah, check out Philip Howard's blog on that.
Okay, so the code is in a blog post, yeah? So I can see it there. On your blog post, am I right?
I'll add it there. I should add it there. I just have kind of similar content to here, but yeah, I should add some of how we handle those result objects.
Thank you very much.
No worries.
Hi, thank you. So it's a quick question. In the additional code you created to handle these callbacks, you have two channels, one for errors and one for the result itself. Mm-hmm. I had to do a similar thing for another asynchronous API, but I used the suspend coroutine function offered by the Coroutines library, and I wonder if there's a particular difference between those two, if there's a significant difference in the way, if I should prefer your approach or mine, depending on different situations.
So yeah, I think you could do it with the suspend cancelable coroutine, but I think we might have to use like nullable callbacks, and we're setting callbacks and nulling them out, which I wanted to avoid. And also with channels, it's a bit more flexible that if you want to change a channel into a broadcast channel, like say for our USB disconnect one, we might want to deal with this in multiple cases or in multiple places. So channels offer you a bit more flexibility from that point of view.
All right, thank you.
Thanks.
Hello. My question is about the channels, basically. So, as we know, the channels should be closed. And at what point of your application, if you initiate the whole thing in the application startup, at what point you actually close the channels, or they stick there forever, or until the app is closed or killed?
So yeah, we keep them open until the app is closed or the card reader is plugged out. But we do have the card reader on for most screens in Toast, even like the login screen. You can swipe to log in. So yeah, we do have the card reader on pretty much all the time.
Okay, but is it impact some memories or anything like that? And also, like I'm not sure, like you're using the channels in a way that the same controller can be disconnected and connected through the application multiple times, or it should be connected once and disconnected afterwards, or like at the application end, basically.
So yeah, for the memory use, yeah, it's something to consider that But I think how we would handle it would be creating a new card reader object and a new controller object. When we if we want to shut down the old one, we can just kill everything and then create a new one with fresh channels to clean up that memory. And yeah, for the controller, so yeah, we do just want one controller. So yeah, I'm not sure if that answers the second part of your
question. It's like the single initialization on the application startup, and then it's live through all, or it can be disconnected in the meantime. Because like this is the answer probably to the question that was asked before: is it easier to use the suspended coroutine instead of channels? And in case it is single initialization, probably the coroutines channel would bring more benefit here than channels.
Yeah, so I guess maybe with the nullable callbacks and the suspend cancelable coroutine, you don't have this kind of long-running channel, so it might be beneficial in that case. But in our case, we kind of wanted to keep it long-running, and if we want to clean it up, we can just kill the whole object.
Yeah, thanks.
Thank you.
So with the channels and the listener pattern, how do you handle if two callees will call get device info concurrently? Will it be a separate listener for each callee, or will it be?
So we actually we enforce at the application layer that it needs to be single-threaded because there's only kind of one card reader, and you can only talk to the card reader can only handle like one communication or one caller at a time. So yeah, we handle that at the caller using a coroutine mutex, which you should maybe put inside the controller just to make it even more thread safe. But we handle it at the caller level at the moment.
Ah, okay. Thanks.
Thank you.
Okay, one more from my side. Do you handle situation when app gets killed, and the device is in some unknown state? You reset the app, and then what?
So yeah, if the app gets killed, we lose all the state, and then yeah, that we can just start again on app startup.
So do you need to assert on the device state somehow, like when it was in the middle of some transaction, then the app gets killed, and
yeah, so
you can recover, like, is possible somehow? Yeah.
So if like the power goes, the power will go to the reader, and it'll be in a fresh state on startup. But yeah, if it's in the middle of a transaction and you can get into a bad state where you'll get errors back, you'll get device busy errors. So we handle some of these differently. Like when we're trying to start the connection, we can retry these connections if we're getting back different errors. But yeah, you can get into states where you'll make a command to the reader, and you'll get a device busy error back.
Thank you very much.
Thank you. Okay, great. Thank you.
Hello, everybody. Thanks for coming. So before getting started, how many people here own a Raspberry Pi? Okay, that many. How many of you have already written some programs to control your Raspberry Pi? Okay, how many used Kotlin native? Okay, that's very reassuring. So today I'm going to talk about something kind of marginal and experimental, and which myself find a lot of fun exploring. So my name is Qian. I'm originally from China, and I work and live in Paris as an Android developer, and I'm also a GDE for IoT. So today, I will start by giving you some context about why I started working with such kind of weird combination of technology, and how I discover step by step how to make it work. So everything started last year. I decided to build something to have fun. So I've been growing up as a lonely child always. So I'm always thinking about building a robot, an adversary to play games with me. So what I was thinking was Android Things was a great platform at the time, and it allows me to have a lot of possibilities. So I started to conceive this installation. So it ended up like this. You can play rock, paper, scissors. So I had the ambition to add the lizard and the Spock too, but they didn't work really well. And you can play with it, and it will play with you at the same time. Then it has a camera which can recognize the gesture the players played, and the user some machine learning. So it runs on TensorFlow Lite, and it can recognize the gesture of the players. Then it can tell you, oh, you won or you lost. So it's a detailed view as you can see. Here's a small demo. C'est parti. There's some game sound.
Press the button to start the game. 3, 2, 1, play. I lost game 1. Rock, precious, scissors, sad face.
So that's my coworker Michael. If he's working the live streaming, he'll probably be surprised. So the project was built by several tools. I built a data collection tool to ask my friends and coworkers to upload photos for me, and for the hardware part, I mainly used Android Things and other server motors. And for the application which runs on Android Things, as you can see, I wrote them 100% in Kotlin, and it runs on Android Things. That is the tools I used to ask people for uploading photos. Then I stored them on Firebase. Then I ended up training them on my own computer, and it's totally not legit if you want to use it in production. And for the hardware part, I used really low budget because Android Things, I've already had it, and the other components you can find it easily on Amazon and other places. So for people who haven't used Android Things, it's an Android-based embedded platform, so developed by Google several years ago, and it's no longer updating. Other than Android Things, I've also used the 16-channel driver to control different server motors. During a weekend, I used my glue gun and some other things I can find at my own place. And I ended up by doing this. So I was pretty happy about the result. I was thinking, oh, I might be able to present it everywhere and have people interested in the Android Things platform. Then 2 months later, Google decided to announce Android Things is no longer in our roadmap. I was like, oh, that's very sad. But since I'm an Android developer who writes Kotlin on a daily basis, I was thinking, why not discover another possibilities? So at the time, I've read an article written by Hadi in 2017, I think. And that's maybe one of the only, or two of the only articles on internet which uses Kotlin native on Raspberry Pi. I was like, oh, maybe I can make it work. So at the time, I have no idea how Kotlin native works under the cover. So I have to try to understand it and discover the how do we say, the doability of my project. So I start by reading documentations. The first sentence you will run into when you read all the documentation of Kotlin native is Kotlin native is an LLVM backend for Kotlin compiler, and it's a native implementation of the Kotlin runtime. a Kotlin standard lib. It compiles Kotlin code finally into the native binaries, which can be run on different targets. So to understand that paragraph, not just literally, but like in a programmer's point of view, you have to have an idea of how compiler is designed. So compiler design, a classical one, contains 3 phases. So there's always a front end, which compiles your code into some sort of intermediate representation. Then it often goes through a middle end, which often is an optimizer. Then it passes through the back end to become finally the machine code. As for LLVM, so I think a lot of people in this room have already heard LLVM. LLVM is one of the most popular compiler infrastructure nowadays. A lot of things are built on top of it, Rust, Swift, and a lot of awesome compilers. And it has an implementation slightly different as the architecture I've just showed you. So it actually uses different levels of intermediate representation to make it work. So how do we understand Kotlin native as a LLVM backend? So starting from the source code, we are going through a transition Kotlin compiler to obtain the first level of intermediate representation. Then the Kotlin native compiler will do the job to convert it into an LLVM intermediate representation. Then it converts to the machine code. So that's how we obtain different native binaries for our different targets. Then I went on read the documentation. So in the documentation, it basically tells you what's the target platform already existed for Kotlin native. There are Android, iOS, Linux, macOS, Windows, WebAssembly, and as you saw this morning during the keynote, there's even watchOS and tvOS now. What's interested in me is the Linux part, because I know Raspberry Pi runs Raspbian, so Raspbian is a Debian-based OS. So I need to know if I'm doing this project, it can run on Raspberry Pi. So some of you might be familiar with what RAM is, what x86 is, but some of you might not be that familiar. So here I'm just trying to have a quick recap on what that is. So that's different kind of architectures. And the majority of our mobile platform and Raspberry Pi uses RAM-based chips. As for Raspberry Pi 3, and we have a typical RAM V8 chips. So at this point, I was convinced that it can work, and it's already supported by Kotlin native. I did another check on my Raspberry Pi, so it's written RMHF, so it means hard float, and it's among the supported target preset, which is Linux RM32 or HFP. HFP means hard float port. At the beginning, I was scared by all this kind of abbreviation because it doesn't make sense for people who haven't had the knowledge yet. Then I started to look into the possibility of cross-compilation, because you can always compile your program directly on your Raspberry Pi, but since it's a little system and it's just going to take forever to finish, so cross-compilation is a better solution if I want to make the project works. So what's a cross-compilation? Cross-compilation means compile your source code instead of on the target machine, but on a host machine with the proper toolchain. In my case, I want to use my Mac, because that's the only PC I have. I have like an old PC, but like which runs on a weird version of Ubuntu that I no longer use. So I want to see if this configuration can work. And I keep on reading the documentation of Kotlin native. So I realized there's 2 components to make these things work. The first one is a Conan C. Conan C means a Kotlin native compiler. And the second one is a C-entrop, means the tools that helps you to create the Kotlin binding to have this C interoperability. And it's actually simpler than a lot of people think. We always start by define a define file, so it's ended up by point def, And we use this tool to generate the binding, and we use the binding to code, and then we compile everything with a compiler into the native binary. And before going into the real code, I read another chapter of the Colin native documentation, which shows the different mapping of C types towards Kotlin types. So I was like, at this point, I should be probably ready to start coding this thing. Then I realized also IntelliJ is supporting it. I was like, oh, everything is aligned, and all the wonders start by laying the first brick. So I should get started. I start to set up everything, find my Raspberry Pi, plug some wires. So that's the first setup looks like. I have a LED, and I have a button, and I have a resistor just to make nothing like burns at the installation. For people who haven't programmed with a Raspberry Pi, so there's a thing called a GPIO, so it's a general purpose input and output. On the Raspberry Pi you just saw there's 2 lines of pins. So today I'm going to explore several pins in my presentation, not all of them. So I'm marking everything out. VCC means where you should get your power. Ground means where you should plug your ground and everything. I think it's like basic electronics, and everybody should know it. I started in February 2019 this year, so I was trying to make it work with the only 2 or 3 articles that I find on the internet, which is very difficult because comparing to other technology, you have like thousands of Stack Overflow posts and everything. It's pretty marginal, and I run into some difficulties right away. So compiler told me the target's not available on your host. So basically means you can't do the cross compilation on the MacBook for your for the Raspberry Pi. So that was the first hit of frustration. Then 2 months later, in April, I started to check the news, and I realized, oh, now it works. Because in the 1.3.30, they actually released the support for that. So that was a moment of relief because I had a conference coming up and everything. So the first step was to make a typical hello world works. I started writing my first main function, a Colin native, which will later on run on Raspberry Pi. And I was thinking, what's a better way to understand how things work by compiling everything manually? So I used the Colin native compiler, and it's actually very simple. You just have to say, oh, my output, the name of my output, and the target name of my target platform. It generates an executable, which ends with .k.exe, and to make it work on Raspberry Pi, you just have to copy it. So I'm doing a simple SCP. And it works. That was the very first Kotlin native application I ran on my Raspberry Pi. So I was like, okay, that works. Let's push the things a little bit further. So I should make the basic GPIO works. So let's start by using make the LED flickering. Before doing this project, I've been using Android things or other Python libraries. So what's the advantage of using those kind of library is like everything is already wrapped. All the drivers has already been provided, and you have nothing to worry about. You just have to call the high-level API functions. But this time, I'm getting a deep dive to the low level, and I have to do it myself through some interoperability. And so I started to look for the library I can use to make this work. As some of you may know, one of the most famous library which works with Raspberry Pi's GPIO is PyGPIO. So it has been used in a lot of Python or other language bindings. So it's the layer below. There's another library called WiringP. So those two are the two C libraries which are most frequently used by the community. So I choose the PyGPIO because there's a lot of discussions on how to use the library, and the documentation on C library is very detailed and very well. I start by create my first PyGPIO dev file. So inside this file, I just have to say what's the header file. Then I use the C interop tool to generate my Kotlin binding. Then run the Kotlin native compiler. So how does that work step by step? That's how my definition file looks like. You just have to say, oh, this is my header file. Then you go on to generate your Kotlin binding. It looks like a complicated command, but if you break line by line, you can see this is my definition file. This is the compiler option which indicates where is the header file. Then it's the name of my output, and this is the name of my target. So when you finish doing all this, it will generate two things majorly. The first one is a Kotlin binding, so it ends up with a klib. The other one is the build folder with a lot of other stuff. So at this point, I have a Kotlin binding which works with the PyGPIO C library. I have to make it at my purpose. So I start to look into the basic APIs. What should I do to initialize the GPIOs? What I should do to give them values or read their values or make them sleep for a certain amount of time. As you can see, this is a C API. It's very simple, actually. You just have to pass the right ping name, you have to pass the right value, and it does the job. And let's have a look at the Kotlin native binding. So the Kotlin binding looks a little bit more complicated. And you can see there are types, mappings happens. So it turns out to blink your LED is not that hard with Kotlin native. Thanks to the article of Hadi in 2017, I made it work in less maybe than 2 hours. That's very important, so it kind of encourages me to keep going. I was thinking, okay, but I have the program which sort of compiles. There's no error, but how do I build the binary that works on Raspberry Pi? So at this moment, the things become a little bit trickier. So to make the library, to make the final binary works on Raspberry Pi, you have to have the right library. So the library should come from Raspberry Pi. So what's happening is I'm building the GPIO library on my Raspberry Pi to generate the shared object. So it's the library here you can see. And I retrieved it for the cross compilation on my MacBook. I lost nobody? Everybody is still with me? Okay, so that's the magic. That's where the magic happened. I used the compiler to compile my binary by indicating what is the library I'm going to use. This is the Kotlin binding I just generated. And this is the library I link, because if you link the wrong library, your binary won't work on the target machine. And this is the name of my output, and we're still targeting Raspberry Pi. And this generates a LED executable, which actually blinks the LED. Everything till this moment was pretty smooth. I get the idea what's the step to make things work. I'm saying, okay, I'm doing a lot of things manually. Let's move the project into IntelliJ. It's more modern, and there's a plugin which supports everything. So the Colin multi-platform plugin not only supports all the cross-platform mobile apps and other stuff, it also supports this kind of weird project. But the thing is, it's still very experimental, and the DSL changes very often. So you have to look up all the samples in the repository to have a better idea about the APIs. The initial configuration is kind of very painful, so I spend a lot of time just to make things work as it is. As you can see here, we can see the name of the target, we can see how the binary is generated by link the right library, and we can see how the interop tools is used to generate the binding. So actually, all the manual steps that I just showed was contained in this small piece of groovies. And then I started to like do a lot of SCP, so like repetitive tasks. So I was thinking, okay, let's automate everything. It's very simple because if you are using IntelliJ and Gradle, there are plugins which does SSH for you. So I ended up writing a small tasks just to deploy everything on P. So what I have to do every time I change my code, I just have to do a Gradle build and deploy on Pi. So that's kind of streamlined the whole process of building this prototype. And I decided to push the things a little bit further. Now I can make the light blink. And how do I intercept the action of pushing on my buttons? So this time we're using another GPIO, which is slightly different because the LED is an output pin. And this time we need another pin as an input. I was thinking, so once I launch my binary, it's actually goes into a continuous loop. So the only way I can actually interact with it, it's by a physical input. So I have to have a callback for my button push. So I go back to C, read the documentation on GPIO. There is a method called setAlert function. As you can see, it takes the name of the ping, then it takes a C function. So far, so good. Until I see the Kotlin binding of this method, I was seeing C pointer, C function, and other stuff. That's the moment I start to panic a little bit. I was like, oh, what's that? And how do we make that work? I kind of find the equivalent between the type def and type alias. As you might remember from one of the previous slides, so everything is mapped to Kotlin kind of perfectly. But the thing is, how do we map a function pointer from C in Kotlin? Actually, JetBrains has already prepared that thing. So there's a nice wrapper called static C function, which allows you to kind of convert Kotlin function seamlessly to a C function. My code ends up look like this. So you just declare your lambda or whatever, and you pass it with the static C function. And it works just really well, except there are problems of sampling rates. If you are a hardware fan, you know the sampling rate is very tricky, and it can vary depending on your hardware component. You have to calibrate it carefully, otherwise it can have the interference and everything. So my callback works pretty well, except it can like have multiple action fired at the same time, which I still try to figure out why. So till now, my LED works, my button works. I want to do some more control over my Raspberry Pi. So I was like, okay, we can try to control the server motor. So the server motor, it's a little bit more complicated because before using server motor, we have to understand what is the I2C protocol. Since everybody here, almost like everybody have a Raspberry Pi, I suppose you have already programmed something with I2C. So it's a protocol which allows a master to control different slavers through the synchronization of clocks. And there are two concepts to remember. It's SCL and SDA. And they are the pings that we can find on all the GPIO pings. So this time we're going to use those two pings to synchronize with the driver and also to give them data. So my installation becomes a little bit complicated. You can see the camera is plugged on too, because I was doing something with the camera too. And to control this servo motor, you also have to understand what is PWM, pulse width modulation. So pulse width modulation is a methodology to apply some proportional control on your electronic signals. So instead of having something really one shot, you can have a finer control over what happens with your hardware component. It's being widely used for servo motors and also LEDs and LCD displays. If I take a typical servo motor SG90 as an example, there are different duty cycles. Duty cycle means when the signal is high. So SG90, normally it has a degree between 0 degree and 180 degree. So if you apply a path width for just in between, you can have the servo motor just wave half of the angles. So that's the basic knowledge I had to have before going into that. And our drive, it has a master chip called PCA 9685. So that's an important name to remember, because when you start to looking for C libraries or low-level libraries, they are normally named with those name of the master chip. I found a C++ library really quickly, but the thing is, it's not working with Kotlin native. There's a huge post on the Kotlin forum about the discussion on whether should C++ be supported by Kotlin native. I ended up finding a small but really essential libraries. So the same steps. I installed this library on my Raspberry Pi. I built the library. I obtained the lib, the shared object. Then I get it back for cross compilation. And this time, the APIs, the API become a little bit different. So this one is for initialization. It's still very simple. You just have to give it the right E2C address, and everything works as it should. But the things become a little bit more complicated when you wanted to control your servo motors by giving them angle values. There are several methods that we can use for the angle values. I'm pretty interested by the first one. So the first one actually asks for a pointer of an array. So that's the thing start to bother me. So how do we pass a pointer of array in Kotlin native? I start to read the code in Kotlin binding. So the Kotlin binding, you can see something called C-values references. That's something I've never seen in my life, and I just naturally panic again. When I go to the API doc of Kotlin native, you can see the C-values reference is actually represents a reference sequence of a C-value. It's actually designed so that a developer, when they use Kotlin native, they don't have to do the memory allocation manually. At the beginning, I don't know that. So I was like, oh, this looks complicated, let's do it native way. And in Kotlin native, there's something called memscope. So memscope is giving you the possibility of having a native placement. Then inside this block, you can do everything a native way. You can initialize your array with the right size and given them the right value. So my first solution looked like this. And it's just almost the C way, but written in Kotlin. Then I find out, actually, Kotlin native has provided other simpler solutions. They provided the extensions, for example, to C values, which allows us to create this self-contained, immutable, actually, sequence of C values. It can be passed around between Kotlin binding and the C level really smoothly. So my second implementation looks way much more Kotlinier. All the way through here, half hours has already passed. I hope everybody's still with me. I started to try to capture images with my camera, which is plugged on my Raspberry Pi. So at this point, I kind of just have no idea what should I do, because I know all the Raspberry Pi camera applications, they run on something really complicated. And there's no way I can find a simple C API that I wanted to do the things I want. So I cheated. I used the binding for the very low level, and I basically run a command line from my program. But that works. And as long as it's the last thing you do before exiting, because it's just going to throw you all the way back to your loop. And after all this, I was like, okay, maybe I should try to make TensorFlow work, but it seems so impossible because, just too far away. Like, how do I make them work together? So I started to look at, is there something in C already for TensorFlow? So actually, there's a C library for TensorFlow, which is supported like on different platforms, but like in the list, there's no Raspberry Pi. there's nothing near that thing. So I was like, stay calm, and we can try to build everything ourselves. So I started like a long journey of trying to build TensorFlow from scratch, from source, with using Bazel. So endless nights. At like maybe 10 or 20 times of failure, I was saying, okay, no longer trying to make that happen. Then I find a Japanese engineer who put all the binaries he built with success on GitHub. So I was like, that's amazing. And thank you, internet. So I write a thank you tweet to him on Twitter. That actually allows me to make things work, but like I didn't push all the way to do the image inferencing because it was becoming more painful than fun. I can load a graph, I can create a basic tensor which does the calculation, because there is a TensorFlow example in Kotlin native library, GitHub. But doing image recognition all the way, that requires a lot of knowledge on TensorFlow. On TensorFlow C API, which is not documented, on Kotlin native, on C, and everything. I was like, okay, I'll stop here. And now I can show you some demos with everything I succeeded in doing. So there's a circular diagram, so everything I've plugged together. And I did some upgrade with Lego. It definitely helped with my mental health. And this is the demo. Sound. That thing it took a long time to work. Then I did some like TensorFlow basic operations. Then there's the cheat, the camera thing. That's it. So that 30 seconds demo took me, I don't know how long to finish, but that was cool. So time to conclude this very ridiculous and funny journey of Kotlin native on Raspberry Pi. What I've learned from the whole experimentation and playing around, so it's very experimental. Don't try it at your place because it's kind of dangerous. Because you risk to start to being nostalgia about like why I'm doing this. I should use other thing, which is more mature. And this, what I used in TensorFlow for C interoperability, it's just the tip of the iceberg. There's a lot of other things you can use, which requires like more extensive C knowledge, which I don't have actually. And the debugging is really hard. So there's actually no debugging tool for Kotlin native on this kind of purpose. And what I was doing just to like print lines. I think that's very effective. And also, since I'm interacting with a low-level library directly, I have a problem with the sample rating, and I don't really necessarily know how to fine-tuning that. So that's made me kind of crazy for a while. But I learned a lot from exploring this, because I learned a lot of things about the compiler again, because in school we try to build our compilers, but that was painful because you don't understand why are we doing this. Now I wanted to write a LLVM backend myself just to understand how everything works, which is pretty amazing. And it was fun exploring. And why I'm doing this, because software is getting incredibly complex these days, and interfacing between different languages is becoming super important. That's why we're seeing so many different talks on multi-platform applications to capitalize our business logic at maximum rate. So I think that's a very good way to start to try to mutualize our works. And also, by doing this, I actually have a low-level control without giving up my high-level convenience. As you can see, we keep working, keep writing in Kotlin for those kind of applications. And the openness of Kotlin native, it's just amazing. And maybe some days we will have plugins for WebAssembly written in Kotlin native that will like just tremendous boost the efficiency. And I also saw some discussions on the internet about a comparison between Kotlin native and Rust. So if you have already played with Rust, you know Rust also uses LLVM as a backend, but it's very different in terms of memory management model. because Kotlin, for Kotlin, it's automated. We have a reference counter and a cycle collector, but for Rust, it's a smart pointer. So everything, the memory, in terms of memory, is managed manually, which gives a programmer better control over memory, but like you have to be there, do the memory thing, pointer and stuff. And also Rust exists longer comparing to Kotlin native, so it has a mature level which is higher. But it stayed kind of in a very tight scope and endured by a lot of people who loves high performance program which have the memory management to the point. And I think in the near future, we'll have more news on those kind of application. This stays as an experiment, but like it shows all the possibilities in the future that we may have. And I thank all these people who did the talks and wrote articles on internet. Without them, I can't make that work. And if you want to check out the code, I put it on the GitHub, so you can take a photo and try to play it with it. It's called Shifumi, because in French, like rock, paper, scissors is called Shifumi, and I don't know why. Thank you, and don't forget to vote, and I'll come back to the slide. If you have any questions, I think we still have several minutes.
So questions? Questions?
You said the debugging is hard, and I can agree. Did you also use the command line debugger LLVM and the Python script they provided?
Oh, I don't know about that. What's that? Yeah, I learn things every day. That's cool.
You can debug Kotlin multiplatform and Kotlin native code with the command line LLVM debugger.
Okay.
And the guys from, I don't know if they are from Kotlin native or Kotlin multiplatform, they provided a Python script that transcribe the Kotlin classes, in example K-string, to something more readable in the command line that you can debug.
Cool. Yeah, I'll try that out, definitely. Thank you.
No questions?
Yeah.
Hello.
Hello. First of all, you also seem to improve your Lego building skills while doing this project. And the second thing, with Rust, you basically, I don't know if you mentioned it, but you could basically opt out of the smart pointer usage and basically maintain all the memory on your own purpose, right?
Yeah, for Rust, it's, yeah. I'm not a huge expert of Rust. I think I write like maybe 2 programming Rust, but you can, I think everything you do, the memory you have to, not free yourself, but like you have to define it in a really specific way.
Yeah, yeah. I wasn't sure if you mentioned that. That's why I wanted to ask, like, if the.
I think you probably have more knowledge on Rust than me. So yeah, I didn't know that yet.
Okay.
Thank you.
Thanks.
What's the first question? Sorry, I didn't catch that.
Oh, it wasn't a question. It was just like, yeah. I was just thinking it's interesting how you were building Lego bricks around all the hardware.
The Lego part, I'm still working on that because Lego actually has a server motor for themselves, but it's very expensive. So that's why I use a glue gun to like build my own server Lego. So yeah, thank you.
Thanks.
Other questions?
Oh, there's another one on top.
Hi, this is Omar. Thanks for the talk.
Hello.
So you try Raspberry Pi. Do you know if there is like an easier alternative, another platform that it's easier to try with Kotlin?
Oh, you mean making Python work with Kotlin
No.
native?
So you try Raspberry Pi now?
Yeah,
but do you know
Raspberry
if there is another hardware platform that we
hardware.
can use?
I think as long as the hardware's, like the chips, the architecture is supported among the target preset, it will work, in theory. That's what I said before starting out everything. So what I suggest is like maybe check with the chips architecture. But I haven't tried with other, for example, Arduino and microcontrollers. All these I haven't tried.
Okay, well, thanks.
Yeah, Raspberry Pi is the only one I tried. Thank you.
Hi. I'm just wondering, have you tried doing anything similar with Kotlin on the JVM, like controlling any hardware, or did you just go straight for the native?
I think I started by thinking about it, because if you tried it with JVM, essentially you're looking for something Java binding with the low-level stuff. And I was thinking, I think I find some library, which is a Java wrapper for controlling GPIOs. But then I was thinking there's Colin native looks way cooler, so I was just going for the shining objects. So I didn't try the JVM possibilities. Thank you. So I think that's all. I'm around if you have any questions, and thank you for coming.
Should I start? Hello, everyone. My name is Ahmed. I'm an Android engineer at Karim, and I want to talk to you about our experience with Kotlin Multiplatform. Specifically, so Karim, for those who don't know, is a ride-hailing application, specifically targeting the Middle East area. And specifically, I want to talk about our Kaptain apps. And our Kaptains Kaptain is what the term we use to refer to those people working on our platform to drop customers off from one point to another. And as you can imagine, Kaptain app has many responsibilities, some of which is trip management. So where should the captain go? Who should he pick up? Metering, so both distance and the time and the route traveled, and keeping in sync with the backend. But the key point here really is that this app directly impacts the livelihood of captains. So captains, a lot of captains do this as their full-time job, and they depend on it. So if the captain can't work, they're not happy. And of course, that's not good for them because mistakes could negatively affect their earnings. So to kind of start from the end as to where we are today with Kotlin Multiplatform, we have over 25,000 lines of shared code between iOS and Android. That includes tests. We've been in production on Android for a year and on iOS for 7 months. In cities with both the iOS and Android Kaptain apps, about 30% of the captains are on iOS. And the iOS team has 5 developers, and the Android team has 11 developers. But of course, this is kind of the end of the story, so I just kind of want to talk about how we got there, and then kind of talk about some of the lessons and things that we learned along the way. So initially, Karim only had an Android-only Kaptain app, and it was outsourced, so the code was not very well written. They didn't actually have a team that actually maintained it. So modifying the code was very difficult, and there were constantly production issues, captains complaining that things are broken, and we kind of have to figure out what went wrong and kind of fix them. And there was no even good automation scenario where we could actually rely on the fact that any changes we made had sufficient testing so that we know everything is good. So learning from kind of the experiences of others, we knew that we couldn't just stop the world and rewrite. We'd have to kind of do an in-place rewrite. 2017, when Google announced official support for Kotlin as an Android, for Kotlin for Android development. So we began rewriting some of the business logic in Kotlin while within the current app. And we built using Redux-inspired MVI architecture, and I'll come back to this a bit later. And in the meanwhile, we were supporting the existing code base. But of course, what you have to realize is that at this point in time, when we started this, there was a new team in place. So there was a lot of fear because we're new to the company. We're trying to kind of change things, but there's highly sensitive code. Not very many people know what should happen or what does happen or what works and what doesn't. And there's no good documentation for a lot of this stuff. Around the same time as we're rewriting iOS, iOS came into the picture when business actually asked for an iOS app for captains. So initially what happened is they allocated 1 or 2 engineers to begin rewriting the Kotlin that we were writing, the cleaner Kotlin version that we were writing into Swift. And this quickly became a problem. So it was difficult to keep up with the changes that we were making. Both of us, both the iOS devs and the Android devs, inadvertently implemented bugs, as you could expect, and made assumptions that weren't very obvious. And it was just very tedious in general. Around this time, we proposed to use Kotlin Multiplatform. This was maybe late 2017, early 2018. So when we approached management about this, they were both skeptical and excited about the possibilities of if this actually works, but skeptical because of some of the other stories about some other companies that with different technologies that they've used. And there were lots of unknowns, especially on iOS. Keep in mind this was very early on, so there was no company we could point to that's in production used it, and especially in such a critical environment. And so the way that we ended up resolving this is kind of by having a risk mitigation strategy. So we sort of said like, hey, today, in order to write this iOS app, the iOS devs unfortunately have to look at the Android code somehow because there's no good documentation anywhere for how this code should work. So if they're going to look at the Android code anyway, why not let's try shipping this multi-platform library. If it works, great. If not, this is just plain Kotlin code with no Android dependencies, we can just very easily migrate it to Swift. They're very close to each other. It's easy to do. And so this sounded like a reasonable risk mitigation strategy at the time. So we began by building a multi-platform library. So we actually started by copying some of these Gradle modules that we were rewriting in the Android app into a new repository. And this library primarily consisted of common code. So a lot of people in multi-platform, a lot of the examples online show an Android app and an iOS app side by side living with the common code. We actually didn't opt for that approach. We took a different approach where we actually built a library. So most of our library is just a standalone library that's then imported by the iOS app and the Android app, respectively. So we worked with the iOS developers to set up and test an iOS build, and we continued migrating code into this library. And in parallel, we kind of extracted out an interface and gave it to the teams so that they could actually start, in the Android case, to rewrite some of the UI, and in the iOS case, to write the UI for the first time. And eventually, we launched, right? So now, I kind of want to shift gears a bit and talk about some of the lessons that we learned along the way. The first one is avoid Android-driven development. Please excuse me because I'm putting on my Android developer hat. This is my, so I'm saying it from this perspective. So for Android developers, it's very easy to convince an Android developer to adopt Kotlin multi-platform because it's essentially what we're doing every day anyway, with very few differences. And so usually when a lot of these efforts are actually brought up by Android developers and pushed forward by Android developers, but being Android-driven unintentionally can actually cause a bunch of problems, and here are some of the problems we ran into. We quickly noticed some chasms building between the iOS devs and the Android devs, and for many reasons. The first is distrust of non-Swift by iOS devs. And the way I like to think about this as an Android developer is the first time someone tells me, hey, how about you write this app in React Native, the expression on my face will answer more than my answer will. So it's the same thing for them, right? Understanding that it's native helped kind of like reduce some of these fears. And ultimately, once they saw it working in production, then that kind of cemented their belief in it. Another problem we ran into was that we were inadvertently, unintentionally working in a silo. This caused problems because the iOS developers felt kind of like siloed out and unaware of what we're doing. And to us, we're like, hey, the repo is open, the PRs are open, you could take a look, but they felt siloed. In addition, if you notice early on when I said that I said specifically we copied code from the Android project into the multi-platform lib, and the reason for that was two things, legacy code and the reliance on some libraries like RX. And at the time, there was no reactive library. There was, and so we were trying to figure out how we were going to address these problems. And so at the time, we just kind of kept a fork, which caused more problems, because we'd update the local copy that lived inside of the Android repo first, and then eventually it would take some time to merge to the actual, what was supposed to be the shared library that iOS team was using. And it was very frustrating for them because they'd be like, hey, we found this bug. And we're like, oh, yeah, we fixed that. But yeah, we'll merge it now. So it was frustrating for them. So how did we kind of resolve some of these issues? The first thing was kind of put better procedures for communicating changes. The first is any bigger change, we asked the developers to write a very short document explaining like the architecture of this change, send it to the other developers, give them time to digest it, and just schedule a meeting where people can challenge the idea and suggest better ideas and so on and so forth. The second one, surprisingly, got some pushback, but in my opinion, was one of the best things we actually did. So typically, our code review process has been 2 reviews. And as an Android developer working, when I had a PR for the library, I would just turn to my neighbor who was also an Android developer and be like, hey, can you review this? Because it was an easier thing to do. So we put this policy, we said, hey, 1 review per platform on the shared code. And initially, the iOS devs were kind of hesitant about this. They're like, hey, I don't really know Kotlin. I don't know if I can actually review this code. But eventually, at the beginning, 1 or 2 of them did. And that actually inspired the rest of them too, as well, over time. And the 1 or 2 that did first were the first to actually contribute to the library, to fix bugs on their own or something like this as well. And then we had a change log with the explicit version changes. So this kind of made it easier to understand what changed between one version and another when we updated code in the library. A couple of things to keep in mind. This might sound very obvious, but iOS developers signed up to work on iOS. And what I mean by this is, there's a piece of this that we actually experienced this actually, where we had one iOS developer who was helping us migrate some of this code into the shared library. And after some time, they're like, hey, I actually didn't sign up to work on Kotlin. I want to work on Swift and on iOS side specifically. So just kind of saying this to be mindful of the goals of the engineers working in the org and empower engineers to learn and grow. And each engineer wants to learn and grow in a different way. And so, that's kind of our job to help our colleagues and managers' job to help the people they're managing to kind of learn and grow, but just kind of some things to keep in mind. A couple of the lessons learned from this. So developing a shared library needs a different mindset. This is especially tricky when you're also the customer, because essentially you're trying to wear two hats. I am the Android dev hat, and I'm the library dev hat. And at some point in time, you'll mix it up and you'll wear the wrong hat. You'll forget to switch the hats. And this will cause a number of bad things, like bad code that you don't want in the library that will be in the library, and things like this. So ideal target is that to make your developers your primary customers. And of course, facilitate iOS devs feeling ownership, because especially initially, it'll be very difficult for them to they'll feel like they don't want to contribute or they're afraid to contribute, and you kind of need to help them feel welcome to do so and encourage them. So when we talk about sharing code, the couple of considerations and things there as well. First, what to share. So what we're sharing today, lots of business logic and rules. So actually all our critical business logic about the Kaptain and how the Kaptain transitions from one state to another, it's essentially a state machine that we're sharing behind under the hood, and it's actually core logic and critical logic, critical business logic that we're sharing. Also the troubleshooting and bug fixing. So this was actually when you start to feel the fruits of your labor, is when the iOS devs are the ones who find a bug, and they find that the bug is in the library, and they fix it, and you get the fix as well for on the Android side, which was awesome. And tooling. Tooling is something we want to invest much more into, but there's huge opportunities for sharing tooling as well once you're actually sharing some common code as well. So some general sharing tips. A lot of people ask, what should we share? And in my opinion, the answer is, it's tricky, it depends. But if you have to give an answer, share as much as possible. But really, the answer should be, share whatever developers on both platforms are comfortable using. And again, going back to the analogy of React Native, so as an Android developer, if I'm applying for a job and they say, hey, our Android app is 100% React Native, that could impact my decision as to whether or not to work on this app or not. So similarly, if you say, hey, we're going to share UI, we're going to share everything, it could also impact an iOS developer's decision to work or not. So share what both are comfortable sharing. Start with what you can agree on, and build trust from there. And this always applies, but study open source libraries and carefully decide whether or not it makes sense to use them at this time or not. Because the reason I point this out specifically is because the great thing is there are lots of new open source libraries all the time that are being built, and those save a lot of time. But initially, some of them might not be very stable, for example, and so there's a risk factor involved. So you have to decide how much risk is acceptable depending on each case-by-case scenario. When we talk about code sharing, we inadvertently talk about dependencies. And there are two primary ways to share dependencies. The first is expect actual, where in the Kotlin multi-platform code, you have an expect class saying that the date has a current time. And on the Android side, you implement it saying, OK, this just returns the current time in millis. And on the iOS side, you say, OK, this is the corresponding call in iOS, which is time interval since 1970. So a couple of points about expect actual. The iOS implementation must be in Kotlin. And so this might not be convenient in the sense that most likely the people doing the iOS implementation are iOS devs. And so you're asking them to write the iOS logic in Kotlin, whereas it's much easier for them to just write it in Swift. the other consideration is the implementation sometimes, because of the interop with Objective-C, might not even look like pure Kotlin that Android devs, for example, are used to. So due to things like allocations and memory scoping and things like that, like some of the code ends up looking a little strange. And so just some points to keep in mind. The other approach is dependency injection, and this is what we do very heavily. So an example of this would be I have an interface in the Kotlin multi-platform code with some methods there defined. On the Android side, I just implement this interface and delegate to some repository. And I can use Dagger as usual, and everything is as usual as normal on the Android side. So I'm just delegating to that repository to kind of get these results, right? And on the iOS side, it's very, very similar. They're delegating to this booking configuration object to get this result, and they're also implementing the same interface. Now, when I actually want to use this in the Kotlin shared code, I can use it something like this. So I take the actual configuration object as a parameter to my class, and I just call it exactly like I would expect to call it. The only difference is that when I'm creating this sample command from the iOS side, I'll just pass in the iOS implementation of the class, versus from the Android side, I'll pass in the Android implementation. Shifting gears a bit to talk a bit about architectural considerations. So first, kind of suggestion, I guess, is limit the impact of changes on the SDK layer. And we kind of learned this the hard way on the Android side, where the iOS side actually did it a lot better. Because of the fact we were actually moving classes out of the Android code into the shared library, we actually for example, moved some of the core booking data classes, which are actually used all throughout the app end to end. Whereas the iOS side said, you know what, we'll create our own local one, and we'll map between this one and the other one. And you can imagine, whenever we needed to actually change that data class, you can imagine the headache it was on Android, because it affected all the code end to end. But on iOS, it was much easier, because there's just one mapping function you had to tweak, and everything was same as normal, right? So ideally restrict usage of the library to a handful of classes, and expose alternative interfaces to the rest of your code so that it makes it easier to adopt changes. Another point is consider whether or not sharing architectures between platforms makes sense. So this is kind of a, there's a difference of opinion about this, but some companies have had success in sharing the same exact architecture between iOS and Android. And just, it's a point of consideration of whether or not it makes sense for your company or not, because inadvertently, your library, your multi-platform library could impact the architecture directly or indirectly. And I kind of want to give an example of this. So I mentioned earlier on that Android library, we initially started with building it as MVI. So when we think of MVI, we think of a stream of states that is observed to, that is subscribed upon, and when changes are observed, some changes on the UI are made. So first off, how we actually did this in multi-platform. So there's actually this neat method in the standard lib, delegates.observable, which essentially just calls, every time your setter is called, it'll just call whatever is in the lambda. And in this case, this is just an interface on a booking state listener is just an interface, which again, in the same way that, that I showed earlier, will just be implemented by iOS and Android, so that they can handle any time the state is changed in this case. Even if this multi-platform, even if this this library method didn't exist, you can do the same thing by just calling a method whenever the setter was called. So on the Android side, you'd implement the listener, for example, creating a subject and on state changed emitting on next, and exposing a stream by hiding the subject or whatnot. One point I want to point out here, something that we found very useful both on iOS and Android side, is type aliasing. So if you notice, the class name is booking state listener, but the interface name is CME booking state listener. And so what we did is we gave a name to all the objects coming from the shared class. We prefixed with CME, which stands for Kaptain Mobile Engine. And so we type aliased it. So even though the class name is actually the same, but because of the type alias, like it's cleaner to use this way. We do this both on iOS and Android sides. The iOS code, again, is very similar. They create their own subject using RX Swift, and again, emit on next whenever the method is called, the function is called. So that's how we observe changes when things change, but how do we actually make changes? To make changes, we just call methods on the library, as you would expect, to just make changes. So using an example, if you were to open an app and request a ride, what would happen is something called a booking offer is created. And this booking offer is sent by the backend to a number of captains who are most ideal to accept your request. And when the captain sees the offer, they can choose to accept it. And when they do, one of two things can happen. Either it can be assigned to them, or it can expire. And expired really just means that either someone else got it, another captain got it, or maybe the customer canceled and backed out, for example. So you can imagine on the Android side, someone clicked the button to accept the offer, and you're just calling this method on something in the shared code on booking offer accepted. And you're subscribing somewhere to this observable of booking states, and looking for a change in the assignments. And whenever something like this happens on the UI thread, for example, you do whatever UI makes sense, UI change makes sense, and the same for expiration. The iOS devs actually wanted to do it a bit differently. So they didn't want to actually be subscribing one place for the assignment and somewhere else for the expiration. So they kind of wanted to do it a bit differently. And what they really wanted was they wanted a function called accept, where they would give it the offer, and it would return back a booking if it was assigned, or it would throw an exception otherwise. And so they opted to write a layer on the iOS side to kind of manage this. So the way this kind of looks like, I know it's a lot of code, but I think it's not. I think the important part is, so they have a piece that's watching for changes of expiration, and whenever such a change happens, they just throw an exception. And another change for watching assignments, and whenever such a change happens, they map the booking object from the library into the iOS booking object. And then they create an observable where they first accept the offer, and then they wait for the first thing to come back, whether the assignment comes back or an exception is thrown, and that's it. And so they just return a single booking. So the reason for this example and kind of talking about this is just saying be intentional about the impact of the design decisions that are made inside of the multi-platform library on iOS and Android. You can imagine in a case where if the architecture on iOS was much, much different, the way that we structured the architecture on Android might have made it difficult for them to actually adopt it. But because things were similar enough, it was straightforward without actually changing the library to kind of adopt what both sides wanted to do. Shifting gears a bit and talking about platform differences. So not everything is analogous between Android and iOS, as you can imagine. So on Android, for example, you can actually request a fuse location, or you can request GPS location, for example. And we're actually requesting both and doing different things with both of them. But on iOS, you just get a location from core location, and you have no control over where it's coming from, for example. So just something to keep in mind, right? So other things to consider is the fact that infrastructure or libraries may differ. And these are things that we kind of take for granted, or we took for granted at least. So just a point of heads up. So for example, on Android, some of our jobs we're using Work Manager, and we kind of treated them as kind of fire and forget. And we knew that if it failed, it's going to retry in the background silently and so on and so forth, using exponential backoff and whatnot. But we didn't communicate this to the iOS devs because we're like, oh, they must be doing the same thing. But they actually weren't, because how would they know, right? We didn't tell them. And so it just happened when they said, hey, how are you handling errors in this case? We're like, oh, our work manager is doing that for us. So just kind of something to keep in mind. And actually, one more point about this. Actually, even other things like push notifications, which are the same feature which are similar on both iOS and Android, there's different capabilities of the platform that might be available to Android that are not available to iOS, for example, and vice versa in other areas. So just something to keep in mind. I want to shift gears a bit and talk a little bit about code organization. So again, I apologize, Android developer hat on again. So Gradle modules, as in an Android world, we know makes a very good basis of separating business logic and helping achieve kind of faster development and testing time, less conflicts between developers, and less contention on the classes that are being changed. And we can use something like the internal keyword to kind of encapsulate certain classes within a module, but not expose them outside that module. So Gradle modules are great. But so what does this have to do with iOS? So on iOS, the target is to have a single framework, a single multi-platform framework, and this is because of current limitation in multi-platform. So building a single framework from a single module is very straightforward. And even from a repository consisting of multiple modules, Gradle modules, it's also straightforward. But when you actually have multiple repositories, things become a bit tricky, especially if you do what we did initially, which is use submodules, because at the time, we didn't really have another option. So keep in mind, this is before the new Kotlin multi-platform plugin, which I guess is not new anymore. But so before this, that's actually what we were doing. So we had a submodule one library had a, even though there was no code dependency between the two libraries, there was the submodule dependency so that you could just build the iOS framework at the end. But with this, with the new Gradle plugin, it becomes very straightforward to have multiple repositories with multiple modules in each repository. And so what happens is each of these Gradle modules will build an artifact. This is what we're used to on the Android side, where you get jar files on Android from each module, and you get klibs for iOS, one per architecture. And so then what you can do is you push them to Artifactory or Sonatype somewhere in Maven where you can use them. Now once you have this, now to build the iOS framework, what you need is just a single Gradle file somewhere, which is kind of like a monolithic Gradle file that's kind of pulling in all the dependencies needed and builds the final framework. And a snippet of this kind of might look like this. So you might notice that we're depending on Karim Kaptain dependency 1.0. So the nice thing is, first off, it's versioned. Secondly, I don't actually have the library code here. I left the project one as an example, but all of these live in Maven, right? So the other nice thing is changes to the shared code cannot break iOS unless they change the version number. So this is kind of a nice thing. A couple of notes. So this monolithic module I'm talking about has to have at least one source file in it, even if that source file is empty and just declares an object or something, because otherwise it won't build. I think this will be fixed sometime in the future. Classes are namespaced with base name and Objective-C, so you might have noticed the base name that you can specify in the module. This actually ends up just prefixing the different class names. If it's not there, it uses the Gradle module's name. And in Swift, classes are not namespaced. So duplicate classes from different modules will have their names changed. So why would you have duplicate classes from duplicate modules? So the fact is, on Android, we can have two classes called core, but they live in different packages. And that's completely fine on Android. But on iOS, there isn't this concept of packages. And so consequently, if you have two classes called core, they conflict. And so what multi-platform does is it renames the classes so you can actually use both of them. So in Objective-C, so remember the base name prefixes the class name, so you'll have like base core and base core underscore. And in Swift, you'll have core and core underscore. So just something to be mindful of. Just be careful not to duplicate names, because otherwise you're trying to use one of them, but you're actually using the other one, and which one, and like the fact that it ends with an underscore might be a bit tricky. So just something to keep in mind. The other point is export is not transitive by default. So if you export a dependency, any dependencies of that dependency, iOS will not be able to see. So you can set this flag if you wanted to be able to see those dependencies. Shifting gears a bit to talk about a couple of notes about building for iOS. So some things are lost in translation. So because of the fact that interop is with Objective-C instead of Swift, a couple of things are lost in translations. One of the things is default parameter values. So both Swift and Kotlin have default parameter values, which are really great, but not in Objective-C. So consequently, something like the copy method, it's there, you can use it, but you have to pass in all the parameters to it. So it's a bit of a hassle right now. The other thing is generics. So, but things are getting better. So imagine you have this class. So this is just a node of any data type, T. And it has a value, and it has a next node. That's it. So imagine I add this into my multi-platform library. What gets generated in the header for the framework is this type ID. And ID is really like any object, essentially. So it doesn't actually realize that it's generic. So when you actually try to use this in Swift, it says, hey, this is not a generic type. You can't do this. Similarly, you might think like, hey, maybe it's because of the T. Maybe if I don't make it, like, maybe if I actually like tell it that like, hey, this will be a node of a car, things will work the way I expected. But again, in this case, I expect value to be a car, but the error is value of type any it doesn't know that, it thinks that it doesn't know what type it is, right? So you actually, without explicitly casting it to a car. But as of Kotlin Multiplatform 1.4, Kotlin Native 1.4, thanks to the work of the TouchLab team, they added a patch to have better Objective-C generics. So when you enable this compiler flag, what happens is, essentially you can see that the ID got replaced with T here, which is kind of what we want. But one kind of thing that we didn't expect is that it's marked as nullable because our initial field wasn't nullable. So now it works, but it's a different error, which is saying like, hey, this value type is nullable. You have to unwrap it. So you actually have to do this for it to work. But essentially, it's working. The reason for this happens to be because of the interop, because of the interop between Objective-C and Swift. So Kevin has a really good blog post where he explains this in great detail. I highly recommend checking it out if you're interested. But essentially, the fix is to just set an upper bound on T to be any. And if you do that, then you get what you would expect. So init with value, type T value. And then, the second example works as expected as well, where it understands that it's a car. So a couple of difficulties. So debugging between Kotlin Native and iOS is difficult. TouchLab, again, has a Xcode plugin that helps with this called Xcode Kotlin that you can check out. And also, like, I guess as we heard in the keynote today, hopefully there are some things to look forward to in the upcoming year. Symbolication is only there for debug builds. Symbolication is important because that's how we know when a crash happens where it happened. It's experimentally there for release builds in 1.3.6.0. And also very recently, the TouchLab team released a library called CrashKit iOS that actually makes it easy for when a crash happens, you can actually identify also where in the Kotlin code the crash happens, as opposed to just knowing that the crash came from the Kotlin code. Want to talk a bit about multi-threading. So coroutines are single-threaded on iOS, but not for long. So there is an EAP version that supports multi-threaded coroutines. And I think there are some apps pushed out that actually use this, especially by TouchLab. But at the time we were building this, so early 2018, there were other options like workers and so on, but we opted to actually multi-thread with delegation and interfaces. So the way that this could look like, or this looks like, is, for example, I have this interface called the booking interactor. And it has a function called handle booking, which is just going to do some kind of network call, for example. And what we pass in is a callback and say, hey, when you're done, just call me back. Give me an error if you have it, or otherwise give me null, in which case I know that it succeeded. Then you can implement this on the Android side. And on the iOS side, you can implement it as well. So you can see here that creating some kind of endpoint, you can imagine service is some kind of network service class that will take this request, execute it, and call the Lambda on the correct thread to do whatever is inside the Lambda, which inside the Lambda will just say, hey, did an error happen? Is this result an error? Is it failure? If so, we'll just create an error. Otherwise, there's no error, and we'll call the callback. Interestingly enough, this code actually was crashing on 1.3.5.0 because of the fact that in multi-threading, access to all mutable objects needs to be single-threaded. So kind of like the core rule of multi-threading is that objects can either be immutable, in which case you can share them across threads, or they're mutable, in which case only one thread can use them. And so this includes object creation, using the object, and releasing the object. All three of these have to happen on the same thread, on the Kotlin native thread. And what was happening, the reason we had the crash there, is because what was happening is, even though we called the callback on the correct thread, after this, Swift was deallocating the Lambda. And our callback still existed there, so it was trying to deallocate our callback as well, but not on the same thread, on a different thread. And that was what's causing the crash. So this was fixed in 1.3.6, but before it was fixed, the other way that you could work around this was just nulling out the object before you return back from the call. And then this way, when Swift actually deallocs the Lambda, it doesn't dealloc your object as well. And another way we could have fixed this probably, but I guess we didn't realize at the time, was to just freeze the Lambda. And we actually realized that, but we didn't do it because we had one mutable variable. And what we didn't realize at the time is that we could have just changed that mutable variable to an atomic reference, which is available on both platforms, and would have just solved the problem for us. So things that we're thinking about at Karim and like we're thinking about now. So our library tests are currently JVM only. And the reason for that is we use mocks heavily. Mock-K doesn't support multi-platform yet, though there's an issue there, and so hopefully we can hope for that sometime in the future. We should have used fakes probably, but we didn't. So, what more can we share besides business logic? Really, the thing I love about this point is the fact that the ideas of things that we should share now are more often than not coming from the iOS developers. So because they're the ones that wrote the newest app, their feature set is less than the feature set available inside of the Android app. So they're like, hey, we want to do this. Is this available? We're like, no, only in the Android app. They're like, hey, what if we just build it inside of the multi-platform library? And this really made me happy because like it shows that after some time, even though there's resistance initially, when they see it working, they're sold on it, and it just makes everybody more productive. Another point is how do we avoid inheriting technical debt? So again, because sometimes we end up migrating from, let's say, the Android feature into the shared library, things end up there that really shouldn't be there. And they're really just there because, oh, Android uses this thing. But really, if you think about it, why is Android even using it? Nobody asked the question for so long, and nobody really knows. So how do we avoid kind of inheriting more technical debt when we're doing this kind of work? I mentioned before common tooling. So one of the interesting things that we wanted to do, and we kind of did a little bit, but we wanted to do more. So I mentioned MVI. We actually log in a very similar format so that in production, when a problem happens, we can just kind of look at the log and understand exactly at which state transition things failed. And you can imagine kind of if we actually are sharing tools, we could actually write a tool very easily to replay exactly what a captain sees on a trip. And not only just have to like scour through the logs to figure out what went wrong, but we can actually visually see it if we actually invest more time into things like sharing common tools. And finally, multi-threaded coroutines. So again, this is going to be huge. It's going to save us a lot of time. So we're super excited about this. So in summary, avoid Android-driven development. Communication is key. It's very important. Give a sense of ownership, especially to the iOS devs, and encourage their participation. Treat your developers as customers, as opposed to treating the app that you're working on as a customer, especially in the cases, by the way, the reason for the whole, in an ideal world, we would have a set of developers that are actually developing the app that are not working on Android and that are not working on iOS. But we didn't have the resourcing to do this. And so we had to take the resourcing from within the existing teams, which is kind of why this ended up happening. But if you're in that position, just make sure you treat your developers as customers. Architect for success, share what both platforms agree on, and then you can build from there. Limit the impact of the shared library on the code. Be aware that the architecture could potentially influence both platforms. A couple of other lessons, multi-platform can be as risky or not risky as you want. And this is kind of the key, like a lot of people are like, it's not ready yet, I don't know. But actually things like the standard lib are like rock solid. And people are using them in production now, and even for mission critical apps, and they work great. Now, if you're trying to use multi-threaded coroutines in production now, well, chances are you'll find a bug. It's still an EAP. It's not even marked as stable yet. So just keep in mind, something to keep in mind. But in general, start small and expand from there. So build trust, and with time, this trust basically allows you to increase your impact. Invest in building and supporting open source libraries, because now is the time. Like now it's a beautiful time, because as more and more people are adopting Kotlin multi-platform, there's a huge opportunity to build open source libraries and invest in them, even if it's just reporting issues when we see them, things like that. It just kind of makes the ecosystem better. One final summary, and small by the way, like we're hiring and we're doing a lot of cool projects, so if you're interested, come talk to me. So I just wanted to summarize all of this in a rhyme. So for engineers at Karim, multi-platform was just a dream. Kotlin multi-platform made it true, and it can work for you too. We share on Android and iOS. Our code is clean and not a mess. Business logic is what we share while showing our iOS devs that we care. Most of our code lives in common main to keep our dependencies nice and sane. Dependencies implemented on the platform side. We use Dagger on Android with nothing to hide. On Swift, we roll our own DI. I speak the truth and do not lie. We build libraries and version them too, updating a changelog with whatever is new, push them to a Maven repo to use, and add a tag with nothing to lose. Klibs are uploaded on iOS, jars on Android without a mess. The clients use them as you'd expect. And best of all, bugs that we detect can be fixed on both platforms with ease, saving us half the development fees. With multi-platform coroutines coming soon, the limits are really beyond the moon. So if you haven't considered sharing code, it's a good time to get into this thought mode. That is all I have to say. I hope you enjoyed this talk today. Thank you.
that talk, but I can promise to look funny. I'm like to introduce to you my co-speaker right now. He has 2 children, so he's building his own binary tree at home. He's planning to learn ukulele, but he promises not to perform that for you tonight. Yeah, he hacks on the Android components, the Mozilla Android components at Mozilla for our Firefox products. Without further ado, Sebastian Kaspari.
Yeah, thank you. Yeah, with me is Colin Lee. Some fun facts about Colin. He was born in South Africa, started developing Android apps on the G1, and is now an Android engineer at Mozilla as well, working on Firefox Preview, our new Firefox for Android. And about the beginning of last year, Mozilla started to split the functionality of its Android browsers into standalone Android components. And at the beginning of this year, we started to rebuild Firefox for Android from the ground up with those components. And in the talk today, we want to talk about why did we do this? Okay, we don't have slides, apparently.
Uh-oh.
I show slides without them.
Let's see if I can...
Oh, there they are.
There, sorry.
That's Firefox Preview, by the way. So in this talk today, we want to talk about why did we do this, how did we do this, then we want to live code a browser here on stage, if the demo gods want to. And then we want to show some of the cool Kotlin language features that made this great to develop. So let's start with the why. For the longest time, Mozilla had only one major Android application that it maintained, and that was Firefox for Android. It's now almost 10 years old, almost as old as Android itself. Then in 2017, we started to build a new browser called Focus for Android, a privacy-focused browser. And it was a completely new app, new repository, new tooling, new CI. We only borrowed some code from Firefox for Android. Fast forward half a year later, a different team inside Mozilla developed something called Firefox Rocket, which later became Firefox Lite, a lightweight browser for the Asian market. And they did this by forking the code base of Focus and turning it into a full-featured browser. Yet another half a year later, a team inside Mozilla looked at developing apps for Amazon devices that also run Android. And the first app was Firefox for Fire TV. Again, it was a fork of Focus, and they turned it into a browser that works well on TVs. And again, later, this was forked into Firefox for Echo Show, for Echo Show devices. And you can already see that this path is a little bit problematic if you continue this with forks of forks. And it just does not scale well. So we wanted to fix that. And some of our goals were we wanted to share code between our apps. Whenever one team builds a cool new browser feature, then we want to be able to use this feature in all our browsers. And we wanted to reduce the maintenance overhead. If we fix a bug in one browser, ideally this bug is fixed everywhere, and we don't need to chase this bug through all the code bases. We wanted to have clear architecture boundaries. Features should be isolated from each other and not interfere if they are not designed to do this. And finally, if we want to build more apps or experimental apps, then this should be fast and easy to do. So we came up with this solution. Let's just build independent reusable components, and then we can use them if we build new apps or if we want to run some experiment with some demo build. But what does components actually mean in this context? For us, it meant we wanted to build independent open source Android libraries. And we wanted to define an Android-first extensible application architecture, which means we wanted to define how you can use those components to build a new app from them. We wanted to have minimal cross-component and third-party dependencies. Whenever you pick up one of the components, it shouldn't mean that you have to use the whole tree of components. And when you pick just one component, it shouldn't mean you need to use some third-party framework that we just liked at the time we wrote the component. They should be customizable and pluggable. Every app is a little bit different, so you need some kind of configuration to fit the component to your needs. But sometimes that's too complex or just not feasible, and then you should be able to replace a component with your own implementation. And finally, we wanted to distribute them as AARs via a Maven repository because that's just easy to consume in any Android app that uses Gradle. And of course, we decided to write them in 100% Kotlin from the beginning. Well, and some Rust code. In situations where we wanted to share our code beyond Android and use it also on iOS, Windows, Mac, Linux, and so on, we decided to write this code in Rust and only add a small layer of Kotlin on top, because then it's easy to use from the Android world. So let's look at how we did this. And for that, let's look at some of the components. And at least in a browser, the most important one is a browser engine. Just to recap, a browser engine usually comes with its own network stack, and it uses this network stack to pull the resources of a website like HTML, CSS, and JavaScript from a web server, and then creates a visual representation of this website, and it's interactive, right? You can scroll it and click on links and so on. On Android, you can choose between multiple browser engines. The most obvious and popular choice is WebView because it's integrated into Android. It is on every Android phone already. Mozilla develops its own engine called Gecko, and we also provide this as an Android library called GeckoView. But there are others. One example is Servo. It's an experimental browser engine written in Rust, and you can also use it on Android if you want to. For some browsers, we use WebView. But for most of our full-featured browsers, we use GeckoView. I want to show some of the features of GeckoView that make this a great choice for at least browsers. First of all, since GeckoView is just an ordinary library, you pick the version and add it to your build configuration, which means you are in control of the updates. WebView updates itself, and that's great for security, but it can also lead to surprises if the engine just changes without you knowing that it's going to change. GeckoView is also multi-process. Websites are isolated from your main app process, and if the engine crashes, you can recover from that and it doesn't need to crash your application. One super cool feature of GeckoView is that it separates between a session or a tab and the view, which means you can load websites completely off screen and later decide to maybe render this on a view. And when you want to switch tabs, like in a browser, you just render different sessions on the same view. It comes with a private mode where it doesn't save any of your browsing session to disk, something that WebView used to have too, but unfortunately it doesn't have it anymore. It supports a limited set of web extension APIs. Web extensions are usually developed by third-party developers to add more features to the browser, and you can do this with GeckoView too. And finally, it comes with some advanced browser features like tracking protection, where it blocks trackers and ads on websites you visit. So let's look at this from the component level. There are multiple choices of engines, which means we want to be able to switch between them or decide which one is the right one for our product. And we did this by defining something we call concept components, in this case, concept engine. And the interesting thing is that this concept component doesn't actually contain any implementation. It only contains the interfaces and data classes that define how we want to interact with an engine. It's basically an abstraction. And then we provide different components that actually implement those interfaces. For example, browser engine system uses the system WebView, and browser engine Gecko uses GeckoView. So this means as long as other app code and other components only use the interfaces from the concept component, it doesn't matter which engine you pick, and you can even switch between them. Another important piece of a browser is the toolbar. It needs at least to allow you to edit the URL, and it also needs to display the URL of the current website. So it's a great candidate for a component. And we followed the same approach. We first defined a concept component that defines how we want to interact with the toolbar, with interfaces and data classes. And then we provided one implementation called browser toolbar, which can be configured to whatever you need. But if the app wants to do something completely different, it can implement this itself. The app team can do this. And as long as they use the interfaces from the concept component, it means it will just work with all the other components without any additional code. So let's assume you use those two components, an engine and a toolbar. Then you might end up with something that looks almost like this. Very big view that renders the website, and in this case at the bottom a toolbar that shows the current URL. I'm omitting some glue code here because whenever the engine loads a new website, it needs to tell the toolbar what URL to display, and if the user types in a new one, it needs to tell the engine to load this website. We solved this by something we called feature components. They know how to connect components together, but for the sake of the example, I will just omit them here. So if you have this, are you done now? Is this a browser? Well, kind of. You definitely can use it to browse the web, and it will satisfy a bunch of use cases. But if you have ever built an app maybe with WebView and you wanted to use some more advanced web features, then you might have noticed that there's a lot more you need to implement yourself. I want to give you just some examples. Maybe you want to handle downloads in your app, and then you might want to show a dialog when the user clicks on a download, or while a download is in progress, you might want to show some notifications. Or if you long press on a link, you might want to show a context menu, showing you options like open this link in a new tab. Or while you are typing in the toolbar, you might want to show results from a search engine or from your local history. Or on media websites that show video content, you might want to use that and show a media notification on Android that allows you to control playback even if the app is in the background. And on websites that have a lot of content to read, like articles, you might want to turn this into a reader view. That is just easier to read on a mobile phone. So what we did is we wrote components for all of those things and for a bunch of more. Way too many to actually show them all on this slide, and way too many for this talk. So instead, let's actually use them to build an app right now.
Awesome. Thank you, Sebastian.
Yeah.
So if you guys have been wondering why I was quiet so long, it's because I get to do the fun part of the talk where I get to play like Diablo or Dark Souls on Nightmare mode by live coding a browser for you right now. You know, there's no better way to show how easy something is than to screw it up in a live presentation. We'll just start just to be daring from a brand new Android Studio project. So the empty activity, let's see, give it a cool name. KotlinConf, I don't know, that's fine. All right. Okay, so I'm going to start off here with a brand new empty activity. First off, we're going to want to give it, let's see, we're going to put in a layout here. I want to put this in a mode where you can actually see what I'm doing. Here we go. Cool. So, can everybody see that okay? I might want to make it a little smaller. It's all right. Anyway, so here I have a layout. I'm going to bring in, everything is way too big. But what you can see here is I have a coordinate layout, and I'm putting in a Gecko engine. Gecko engine is a instance of our browser engine for Firefox browsers. It's using Gecko View, the new, faster engine that we have. We're also putting in a browser toolbar and just two buttons, back button and a forward button. So the first thing we're going to require is we're going to have to bring in a bunch of dependencies. First off, we have these all project repositories. We're going to need some Mozilla Maven repository so that we can access all of these open source components from Mozilla. Then I can go over to the app, and here I'm going to add in a Java 8 dependency. If you don't do this, by the way, things won't work, so please remember to include Java 8 because we don't want things to silently fail for you. And we'll put in our first batch of components here. So, no, that's not it. So I added a concept engine. I added the Gecko engine. I added the browser session concept. Sessions are tabs, essentially, in our browser. And then I added toolbar, which has the concept would be like the interface in this case. And then we have the actual toolbar and feature. So at this point, all we need to do is go over to our main activity. And we need to actually add in the things that we need. Sync Gradle before I do that and add some components. So right now we have, I added an instance of the concept engine, a browser store, which is essentially a MVI or Redux style store of our browser related state. There's a session manager, which is, sorry, that stuff's in the beginning of the way. Session manager is what manages our tabs for us, and session use cases would then allow us to control creating and destroying tabs, for example. Finally, I'm creating an instance of the app just to access this, because I'm not going to do a Dagger thing live on stage for you right now. That would be truly crazy. Let's go ahead, and I think I just need one more thing, and I can actually run this. So we're going to want to create a session. What I did is I warmed up the engine. Oh, this is really, let me see if I can fix this. One sec here. Font sizes are massive. Can't see anything. Okay, Control-Shift-Escape. One sec, guys.
That's actually big enough, maybe.
You can read that okay? All right, we'll just leave that mode altogether. We can read it that way. There you go. So I added an engine and I'm warming it up. That's just doing initialization stuff to make sure that we're ready. You could do that easily in application on create. But what we're doing then is we're going to create a session, a engine session, and then render that to this view. This is referencing the actual Kotlin synthetic engine view. And finally, we're going to add a session to the Mozilla website, select it, and pass in the new session I created here. So this is all it takes. There's one more step I forgot, and that is I have this demo application. I'm just to get the dependency injection right, I'm going to put that on the manifest and name my application. And this should run. Moment of truth. Oh, I got to do one more thing. Let's show the UI. I think it's running. Okay. Just compilation is a fun thing. Anyone know any good jokes? Here we go. And if everything works out fine, it should pull up the Mozilla webpage once the Wi-Fi kicks in. And there we have it. We have the basics of a browser. Now that's not very exciting. I can't actually, it's not using the URL bar yet. At this point, the backward and forward buttons aren't wired up. So let's add in some toolbar support to this sucker. Make it something useful. First off, I'm going to add in a couple more features. This is a toolbar feature and a session feature. I'm going to then create instances of them here. All I'm doing is I'm passing stuff to the constructor. It's very simple. I think that the components in general are fairly easy to just wire into a program. We want them to be easy for you all to use. At this point, I need to have a way to start and stop these features. There will be a better way to do this. I'll show you in a second. But for now, we're going to do it with actual direct calls to onStart and onStop. In addition, we're going to add some buttons. So we have listeners to go backward and forward in your history. And at that point, I think we can demo a toolbar working. And watch for it to load again. Here we go. So you see now the toolbar is actually showing URLs. It's showing lock icon. We're getting, the ability to browse backward, forward, all that fun stuff. So all of that is now working. We can actually type things into the URL bar, and it should browse to them. Sure, something. Anyway, so let's try and do something more interesting. We have these capabilities we've added to our tools. We can add tracking protection. We can add a reader view. And I'm actually going to add something we call the awesome bar, which is basically just a nice search bar that allows you to, say, automatically include your clipboard competence or your auto-completion or other kinds of things. Searches from past history, that kind of stuff. You can add providers for each of those. So that's all working fine, dandy. We're going to jump over here, and we're going to add in some more components. Oh, great. Cool. If you're wondering why they're not up to date versions, it's because you practice with a particular version and then you're like, this one works. These tools are an open source and they're very, very active development. We're adding new stuff all the time. It's really cool. So I add some more missing dependencies here. Let's see. I'm going to add in some components. Cool. So what I added was, obviously, we still have an engine, but now we're specifying a tracking protection policy. So that'll define how we decide whether something is a tracker or not and block it. In addition, we're going to have a request interceptor, which this will be fixed soon. There's a PR to work around, remove this workaround so things will be fine. But for the time being, that's there to enable tracking protection. We have a client. This is just an HTTP client. In this case, we're actually using GeckoView itself to provide that. We already had the store. We already had Session Manager. So we're adding some new use cases and a thing called Search Engine Manager, which allows us to manage the searches that run through your browser you're creating. So all of that's now wired up. We're going to, by the way, the tracking protection is a big deal. I don't know if you guys are familiar. There was a study recently that found that the top 500 websites on the internet are actually run 2 times slower as a direct result of the trackers. So if you can reduce the amount of tracking, it's not just a privacy benefit, it's also helping us in terms of the speed at which we load sites. So I'm going to actually sync Gradle, and then we're going to add a new layout. So all I've done here, I've added this browser awesome bar thing, which is going to render the auto-completed searches as well as things like our clipboard provider. Again, we still have the engine, we still have the browser toolbar, but I've added the ability to a read button and a font button on the bottom of our very ugly UX that I've been using for this quick, dirty demo. So I'm going to move on here a little bit. We could do something nice now. I mentioned before we don't need to call on start and on stop for every single feature that you put into your app. That's because we added some Android architecture components that uses the life cycle. So I'm going to add these view-bound feature wrappers, which now requires that I go back here and set these up with the life cycle. Cool. I'll do the same thing here. And at this point, that I can remove the on-start and on-stop because it's handled. Sure. And I'll go down there. Cool. All right. That's great stuff. I'm going to also now add in the feature for the reader view. Again, reader view is a feature that allows you to look at, let's say, a news article and strip away all of the junk and cruft that's making it hard to read, and just look at the article directly. So I'm going to add that in. See, that's what you'll notice here is because of Kotlin, of course, I passed in a Lambda. This one is actually telling you what to do when the state of whether the page is readable or not changes, and I'm changing the visibility of the buttons in that case. Let's see. So we're going to wire up the buttons now that I just added. Oops, one thing. I think I need to replace that entire unresume here. There we go. So in addition to our back and forward button, we now have a read button, which will then either show the reader view or hide it, depending on the state. And we have a read controls button, which will then show the controls when we click on it. And I think we're just about ready. We'll see. I'm going to set up the toolbar as well up here. Let's add a new function. This one's a little bit longer, so I'll explain for a second. Awesome bar feature, again, is the thing that controls our, as providers for search, history, clipboard, things that can auto-complete into little chips on your display as you're typing. So we're adding a search provider, a clipboard provider, and a session provider. The search, again, is like your autocomplete chips at the top. your clipboards, obviously your clipboard. The session provider allows you to type in something that would match your current session or another tab you have open, and then move you to the existing tab. So that's really handy to have in any browser. Toolbar autocomplete is actually the autocomplete inside of the toolbar, so if you're typing a recognizable URL like google.com, it'll autocomplete that pretty fast, rather than having to look up and pick a search result. And just hit enter right away. We're adding an extra display indicator for tracking protection, so we can now see whether or not we're being tracked on a site. And finally, there's a fix me at the bottom. The only reason I put that code in is because at the moment we'd have 3 icons that are identical for tracking protection as a default. And we're going to fix that default. There's an issue and it's being worked on. So I'll do one more thing. I'm going to add a backpressed listener. And this is going to defer to our features, call their backpress listeners, and if they all come back false, we're going to actually go backwards out of the app. So finally, I'm going to hit the magic buttons, jump back to the screen, and we'll have a moment of truth again. We'll demo the awesome bar and see if it actually turns out to be awesome. I mean, obviously this isn't complete, but we are like role-playing the real development experience of working without Google and Stack Overflow. Here we go. All right, we can now go to, I think there's a link down here that's readable. It looks like an article. So I'm gonna click on this one. And now, if I hit read, it's going to jump over to that. Somebody use the mic. I can actually change fonts, change backgrounds, all kinds of fun stuff. That's great. But we also added an awesome bar. So I can go to, let's say, CNN.com here. Wonder what happened there. Well, anyway, let's see that again. Looks like something didn't get wired up here. Oh, the setup method. Let's see. I made a method. I never called it. Thank you. Thank you. See, this is why live demos are always fun. It's Mark Gray, and yes. I guess the nightmare mode player character just got destroyed. So. Here we go. All right. So we've got this little red X here, which is telling us that's just the thing I added from the Android framework itself to say that there's no trackers at this point. If I go to CNN.com, now we're getting those little chips on the top. If I were to search for something, if I had something in the toolbar, it would show up there. Also, if I had an existing session, I would find it as well. So I can click on these things, and that comes up. And if I actually go in here, you should see a tracker icon change. There we go. And everything seems to be working now. So there's one other thing I wanted to do. Let's actually, now that we've used all of these fun components, let's actually try swapping out the entire browser engine underneath all of them. So I'm actually going to go back in here, add another Gradle dependency. And sync. And then I'm gonna change in the layout. Actually, if you use the generic engine view, it's a little nicer, but then you also have to override onCreate view. So I'm just gonna do this directly. Again, quick and dirty, like I said. And then I'm going to change the engine down here in the components from Gecko engine to system engine, which is web view. And now, if I run that, drum roll, please. It's loading. Okay. You probably noticed that there was a slight difference in the tracking stuff, but because of the lists that they use are different with the different browser engine. However, you'll see that all of the features that we now have in the browser are working as you'd expect them to. So yeah, all of these things that you can put into your browser are very, very easy to include. I pulled it off pretty easily with just one little minor missed call. So I'm going to hand it back to Sebastian to finish this out.
Awesome. I guess I owe you a beer because there was no crash. Awesome. Yeah, for the end of the talk, I want to show you some of the Kotlin language features that made this great to develop. After all, that's KotlinConf here. So my personally favorite feature of Kotlin is explicit nullability. It's just so super helpful to be able to explicitly define whether you take in null as a parameter or whether you're returning null, especially if you're writing a framework and if the teams that are using the framework are different teams than building the framework. For some of the other language features, let's look at how we handle state in our app. And we are using a kind of Redux style pattern. We wrote a component for that, surprise. It's called libState. And in this component, we have a store. And the store contains a state object. It's an immutable state that defines the state the app is in. And the state is just a data class. It's a very concise way to write this immutable state. And it's kind of a tree if you have multiple data classes inside data classes. Of course, the components and also the app needs to know about the current state, and we needed some kind of mechanism to get the current state, but also all state updates. And we did this initially by writing a very verbose but flexible API that we called observe manually. You provide a function that will get invoked with the current state and all further state updates. Then return a subscription object that allows you to resume, pause, or cancel observing the state. And if you use this API, it roughly looks like this. You call store.observe manually, you pass in a lambda that will get invoked for every state, and then you update UI or whatever you want to do with the state. And then at some point, you call unsubscribe. I mentioned this API is very verbose. It works in a lot of use cases, but it's not nice to use. So we looked at options to make this better. Extension functions were a great language feature for that because it allowed us to keep the store as is, plain and simple, and then have those extension methods to iterate on API. So one of the first options we tried is let's pass in a lifecycle owner because then, well, we can cancel, pause, and resume automatically, and you do not need to care about this. In some situations, we noticed that it's very hard to get access to the lifecycle owner deep down in the code, but often we had access to a view. So another API we tried is using a view, and whenever this view gets detached, we automatically unsubscribe from the store. I mentioned that the state is immutable. The missing piece is that, of course, the state still needs to change somehow. And that's possible by the component or app code dispatching an action on the store. For the actions, we used sealed classes. Sealed classes were a great choice because that just limited the options. And we could define the actions we wanted to support. And an app couldn't just invent random actions that we don't support. If we now look inside the store, whenever there's a new action coming in, the store takes the current state and this new action and passes it to the reducer, and the reducer will then return a new state. And the store will keep a reference and also notify all observers. If you go one level deeper, the reducer is just a fancy name for a function that takes in a state and an action and then returns a new state. As I mentioned, we used sealed classes for the actions, and that was quite nice with the when statement here because it forced us to always process all actions. And whenever we invented a new one, the compiler would actually tell us that we need to implement this here. I mentioned the state is modeled with data classes, and that was great inside the reducer. The state is immutable, so we need to create a new state. If you need to create a whole tree, that can be quite painful, but Kotlin allows us to just use copy and then provide the property and value that we want to change. Type aliases, super simple language feature. We use functions. We also use generics because it's a component that needs to be used in multiple apps. And if you mix that with passing generic functions as parameters to other functions, then it gets very hard to understand and read. And just giving the thing a name makes it just much more readable. So we noticed that in 99% of the cases, I guess, when we got a new state, we wanted to update UI. And initially, we did this by dispatching a coroutine or launching a coroutine on the main dispatcher. But if you do this for every state change and you launch a bunch of coroutines, and especially if they suspend in between, then it gets really hard to understand in which kind of order they are getting executed in. And if you want to update UI, then the order is actually very important. So we looked at other options, and again, used extension functions, because this meant we didn't need to pollute the store with all those new methods. We could try those new APIs without touching the store. So the first one we tried was channel. That worked pretty well. We could launch one coroutine, read values from the channel, and process them in order. And then there's no problem with the order, because it's just always the right order. Later, when the Flow API became more stable, we switched to Flow. It was just a nicer API for us, and we could make use of all those new operators. But still, we noticed that it's always the same pattern. We create a new scope, we launch a coroutine on the main dispatcher, then we ask for a flow, then we process the flow, and at some point we cancel the scope. So we again created a helper and tried to find a better API. In this case, something we called flow scoped. In this case, we don't return a flow, but you instead provide a function that defines how you want to process the flow, and then we create a scope, launch a coroutine, ask the store for the flow, and pass it to your function. And then we just return a scope because you as the caller still need to define when you want to cancel the whole thing. I mentioned that Flow comes with all those operators, and that is great. We noticed for state updates, we often wanted to have something custom. And one of the examples is that we have multiple listeners to the state, and we don't want to always do something, but only if a part of the state changes that we are interested in. And one of the things we tried is this if changed operator. In this example, we get a flow from the store, we map it to the title of the selected tab of our browser in this case, and we only want to do something if this title has changed. And then in collect, I get the title and can do something like update the UI with it. That was good enough for simple use cases, but in some situations we wanted more from the state, more information about the state whenever the title changed. And that's why we introduced another version that takes in a transform like map. And in the example below, we get a flow from the store. We say we only want to do something if the selected tab of the title of the selected tab has changed. And then on collect, we get the whole state object and not only the title. In some situations, that could become very complicated. Like we created this beast called filter changed. The best way to explain this is to look at the example. We map the state to a list of tabs, and now we are only interested in the tabs inside this list that have changed. And that's what this filter changed operator does. We map every tab to its title, and then in collect, we will only get the tabs where the title has changed from the previous state. We are almost at the end. So we are 2 people here on stage, but a lot of more people have contributed to this. A lot of teams inside Mozilla, our open source contributors, and I just want to say thank you here. If you want to know more about our projects, those URLs at the bottom here are a good start to know more.
I'll just say briefly, I think like it's very valuable. We love your contributions, and actually we will love to hear about it if you build something using this. certainly we have all these components, and there's a ton of them, and some of them aren't even browser related. So if you find yourself needing metrics or or telemetry, or if you want to have experimentation frameworks, we have all of this in our components, and we love to hear about things you want to see improved.
Yeah, definitely come to us. And if we have a little bit of time left, then we are also happy to answer questions if there are any.
Any questions? Up there.
Yes. Is there a similar project for vanilla Kotlin in like JVM, not in Android, that you're working on?
No. Like in this case, it was Android first and only Android at this time. And we cheated. There are some components that could work on the JVM, but we built AARs for all of them, so we only focused on Android.
The pieces that are cross-platform were built in Rust, and so we have components built on top of Rust using the Kotlin foreign function interface, and those pieces could also use the Swift FFI as well. But we don't have, for example, an iOS or a desktop version using Kotlin at this point.
All right, thank you.
your mic. Oh.
Hi, everyone. We're going to get started. Thanks for coming to our talk. I know this is like almost last talk of the day, so thanks for showing up. Today, we're going to be talking about scaling server-driven UI with the power of Kotlin. I'm Laura Kelly. I'm a software engineer at Airbnb.
And I'm Nathanael Silverman. I also work at Airbnb as a software engineer. We're both on what we call the design language team at Airbnb. And so we build the UI infrastructure that other engineers use to build Airbnb's Android, iOS, and web apps. And so the central goal of our team is to enable fast, high-quality product development. And so for the next 30 minutes or so, we're going to tell you about some of the projects that helped us do just that. So we'll start by taking a quick look at Airbnb's products and some of the bottlenecks in their development. Then we'll briefly look at Airbnb's design system and how it provided a partial solution. We'll see how this design system set the stage for server-driven UI. We'll talk about what server-driven UI is, its benefits, and some of its major challenges. At this point, we'll be ready to introduce Lona, the server-driven UI solution that Laura and I have been working on for over a year now. And last but not least, we'll talk about how Kotlin enabled all of it.
So before we get into the technical details, I'm going to talk a little bit about how we got here and why we started thinking about scaling UI development practices in the first place. A few years ago, Airbnb was quite different. Airbnb started as an accommodations business. We offered one product, homes. At this time, all our engineers worked on supporting that one product. But in 2016, we did something that radically changed the scope of our business. We introduced experiences, which are activities led by a local expert. This changed Airbnb from just being an accommodations app to being a full-fledged travel app. And since then, we've added more features to the app. For example, we introduced Airbnb Plus, which is a curated set of thoughtfully designed homes with standard amenities. And we also added Lux, a luxury tier of homes. We've been adding many products, and we needed to scale our infrastructure across products and use cases to match this. Additionally, our product engineers were building all of these products across 3 different platforms because we have an Android app, an iOS app, and a web application. So whenever we built a similar screen, we were also having to build that screen across 3 different places. And finally, as Airbnb was growing as a product, our engineering team was also growing rapidly. We had many engineers joining who needed to learn how to use our infrastructure, but our product teams were growing faster than our infrastructure teams. Our infrastructure team remained pretty lean. So at this point, we needed to enable rapid, complex development in our applications. We needed to scale our development practices to fit all of these different constraints. The first thing that we did to support this was build something called the design language system. And now Nathanael will talk a bit about what the design language system is.
So Airbnb's design language system, or DLS for short, was created about 4 years ago. And it's basically just a collection of guidelines for designing screens inside the Airbnb applications, regardless of which platform we're designing for. And like most design systems, we have guidelines around the use of the Airbnb logo, or things like colors, or typefaces. But one of its more innovative concepts is row components. And it's a level of abstraction that is unusually high for a design system. And I'll illustrate this with an example screen. So here are parts of the Airbnb listing detail screen. This is a real listing. And some design systems at their very highest level would provide guidelines around all of these elements. So the system would help you design these individual elements, and maybe would have some rules about how you position them relative to one another, and you would compose them to create a new screen like this. Repeat with every screen you need to create. And so, of course, Airbnb system also has to work out all of these details, right? But it goes just a little bit beyond by defining rows. And so constructing a screen with DLS ends up looking more like this. So here we're just stacking row components in a single vertical dimension. And many of these components already exist, and we reuse them across the application multiple times. Now, do note that this concept mainly applies to mobile. Desktop layouts get more complicated, as you might imagine. But this is how Airbnb's mobile applications are built, and they contain hundreds, if not thousands, of screens that follow this pattern. And so by providing reusable row components and other resources, DLS helps with speed. But there's still room for improvement. One of the major inefficiencies is that we still have to build each screen separately for each platform we support, Android, iOS, and web. And unlike web, which can deploy its changes instantly, Android and iOS changes can take days due to the App Store approval processes. Now, quality and consistency have also improved, of course, since we're reusing the same components across the application. However, again, since each platform is a separate project, they're not always on par, not always on sync. And so there have been several initiatives at the company to try to further improve this situation. And the vision is always the following. Can we build screens once for all platforms? And I think there have been many talks today about how to do this in various ways using Kotlin. And can we deploy the changes instantly to clients? And so many of the solutions that emerge within Airbnb were variations of a cross-platform, server-driven system. And we generally refer to those as server-driven UI. And Laura's now going to talk a little bit more about this.
Okay, so now I'll define what we mean by server-driven UI. But first, in order to define it, let's talk about what is not a server-driven system. So here, this is kind of a typical REST API response. You've got an object with a name, you've got an object with a location, and that will have things like an address, country, and so forth. You've got a website object and some photos, which might contain some URLs or UUIDs. So in this typical API response, your client is receiving objects like location, and then it has to take those objects and glean pieces of data into them and then somehow interpret them into a UI component. So hard-coded in your client somewhere, in each client that's consuming this response, it has to know, okay, I'm going to take that address and I'm going to put it in my map UI component. So this is not server-driven. In contrast, a server-driven API response at a high level might look something like this. We would have a carousel object, which maps to a carousel UI component, a title row, an action row, and a map row. Server-driven UI is when the API tells the client what components to render and with what content. Effectively, the server is sending up instructions to the client about what to display. The client has no idea what data is in these instructions. It doesn't know that this is a location object. It just knows when I see a map row, I'm going to render a map row. And so now if we decide to change something in our UI, we can just change that API response and change the action row and title row order. And very similarly, if we change our mind and want to just have a totally different UI component here, we would change our API response to have a different component, like the button row. And now every client that's consuming this API response is going to change instantly to reflect that. This is pretty huge on our native clients, Android and iOS, because as Nathanael said, normally we have to go through an approval process that can take a while. So this is fantastic for our native clients. As long as the client supports the type of row that we're making in that API change, there's no review process, we just change the API. Now, I'm showing an example here of server-driven UI in which the API is on a component level. Let me explain what I mean by that. So you can think of server-driven UI as a continuum. And on one side, you have like different implementations. You have an implementation where the client is going to be implementing it. So an example of this would be that REST API that we were looking at. the client is going to almost solely decide how this API is implemented on the client side. And then on the other end of the spectrum, the server might control every aspect of your UI. So a good example of this is HTML. In an HTML layout, every pixel might be controlled by the server because it controls what in the layout gets sent to the client. Somewhere in the middle, we have component-based server-driven UI. The client still controls some of the fine-grained details, like for example, the exact placement of a button within a component would be left up to the client. But what is shown, like which components are shown and in what order, is determined solely by the server. Because Airbnb already has a powerful component-based design library, we chose to use components as the basis of our server-driven UI. In our system, our design language system components are the building blocks. The client implements them natively, so the details of how they're actually implemented are left up to the native client. But the server tells the client which components to display, with what order, and with what content. Now I'll show you a specific implementation of a JSON API response that we use at Airbnb in a server-driven system. We built a server-driven system internally called Lona for general-purpose server-driven UI. Let's take a look at what the JSON format looks like for this system. Okay, so here we're specifying a really basic component. The first thing to note is that there's a type here, and the type is my component. This is telling the client which component it needs to render. Then we've got some content here, so we're going to send up a title and a subtitle to place in that component. And let's say that we want this component to be interactive on the client. We can specify that too with something called an action. In this action, we're going to designate an on-press action that happens. And in this on-press object, we have a couple different things. We have the case, which is also sort of like a type. In this case, we're going to specify a deep link, but you can imagine there might be many options for this. So in our system, we could have dismiss, logout, or an async request. And then because we chose a deep link, we also need to send up a URL as some data to accompany this so that the app knows where to route when we tap on this row. So this is a very basic specification of how we specify a component in our Lona system internally. Now, once you have an API format like this for your server-driven system, there are still a number of challenges that a good server-driven UI system should address. The first one is versioning. Okay, here's a common scenario. You launch your new server-driven system and you have some initial components. Then time passes, you want to launch a new feature, so you're going to add a couple more components and some new properties. You push those changes up to your clients and you release a new version of your Android and iOS app. Now you turn on the API. So what's wrong with this picture? Well, a lot of users don't update. Just because users don't always have their updates turned on automatically, so you may have some version of your app out that's really old for a long time. And for native apps, this means that there's usually going to be many different kinds of your app out in the wild at any given time. But only a few of them are going to be able to understand the newest version of your API. In other words, your API is going to move fast, but your clients are going to update slowly. A good server-driven system needs some way of keeping track of this. It needs to accommodate an API that evolves faster than its users update. A related issue is keeping clients in sync. So in a server-driven system, it's challenging to make sure all of these disparate platforms are rendering the same thing and supporting all aspects of your API as it changes. Another thing that we found to be an issue is scaling. So remember that we have those 3 different tiers of homes. Even within our design language system, these 3 tiers of homes all have pretty different components that they display. It's almost like each product has a design system within a design system. When we first started using server-driven UI, the way that teams dealt with this is they would build a different server-driven platform for each of these different use cases. In fact, we ended up with over 10 different specific types of server-driven systems. It was a lot of duplicate engineering work to rebuild a system every time you needed something for a new use case. And you might think an easy way to get around this would just be build one system that supports all components in your component library. But this also has its downsides. So in the world of web and Android, features can be delivered dynamically. The app downloads the feature code as the user tries to access it. Of course, this is the default way of accessing a feature in web, and it's now a feature of Android as well. So the user is waiting while the feature downloads. So it's critical that the downloaded code is minimal. We don't want to ship the entire component library that could possibly be supported in the entire app for this reason, because we don't want users to be waiting for a gigantic download. So this is a challenge in the server-driven paradigm because you also want to be able to support all these different use cases, but without this performance hit of downloading every single component when you're just trying to display some of them. And finally, documentation is a really big challenge of this server-driven paradigm. A widely used server-driven system is going to be constantly changing, and even a simple system will have many different permutations of supported platforms, supported app versions, and supported features. So it's really crucial that engineers can be able to predict that when they launch a feature, it will actually work, because it will have direct consequences if they get that wrong. So it's important to keep documentation up to date as the API changes. The Lona JSON format alone that I showed you earlier doesn't solve any of these challenges. That's just part of the picture. But thinking about these common difficulties that we are seeing across other server-driven systems at Airbnb, we came up with a solution for Lona that addresses all of these. And now Nathanael will talk a bit about how we address these challenges with something that we call the Lona spec.
Thank you, Laura. All right, so we knew right from the get-go that Lona would interact with at least 4 systems, right? Android, iOS, web, and the backend. And each of these systems would have to share a common understanding of what's available in terms of components and other things. And so the backend needs to know which components it can send down to Lona clients, and Android, iOS, and web, as the clients, they need to know which components they're expected to be able to render. And it's easy to imagine how disastrous it could be if these systems are not in agreement for whatever reason. For example, say the backend believes it can use a given component, but the Android client doesn't know about it. Suddenly a part of the screen is missing, or worse, the application might be crashing. So we knew we needed a source of truth, and it wasn't just a simple list of component names. As we've seen in the Lona JSON format, each component includes a list of typed properties. We also need to keep track of all the versions of the spec which are available. Components in Lona support events and actions, as well as logging and styles. And we actually won't go into the details of all those features, but suffice it to say that the Lona spec needs to keep track of a lot of different things. And so as these requirements became apparent, we turned to Kotlin for 3 reasons. Number 1, I was tasked with writing the prototype of this spec, and I'd been using Kotlin on Android and some smaller projects for a few years already, so I felt comfortable using it for this. Number 2, we knew that other engineers on other teams at Airbnb would need to contribute to this project regularly for their own feature development. And so Kotlin already has a strong presence at Airbnb among the Android team and a growing one among the backend team. Funny story, in fact, about a year after we started using Kotlin on Android, a backend engineer who had transitioned from working on Android wanted to convince his new teammates on the backend team to switch from Java to Kotlin. So what does he do? Well, he sends a poll to all the Android engineers, and he asks the question, would you go back to Java if you could? And so the answer, as you can see, was a resounding no. And so we also have anonymous Kotlin heroes in our offices who post Kotlin lessons in restroom stalls. So they're titled Kotlin on the Potty, and the lesson changes every month. So we were very confident that a significant number of engineers at the company would be able to easily contribute to a Kotlin project. And reason number 3 for picking Kotlin was its DSL features. So it's great if new contributors already know the overall programming language that you're using, but getting up to speed in a new code base can still be very challenging. And DSL, if you haven't yet encountered the term, means domain-specific language. Kotlin has a feature called type-safe builders that's extremely well suited to creating DSLs. In fact, I'm betting most of you here have heard of them before, probably use them as well. And so we thought that a DSL would help us keep our code clear, succinct, and self-documenting. We also knew that it would be easy to extend it as we added more features. So this is what we came up with. So we start with a component function to add a new component to our spec. And of course, it can be repeated to add multiple components. The first parameter is the component type. It's its unique identifier, if you will. And the second type is a type-safe builder. Now, the type-safe builder creates a component block, and inside we can add a description of our component for documentation purposes, just explaining when and how to use it. And we can also, of course, define content properties. So here we're adding a title property to our header component, and all we need to do is specify its name and type. Content properties also have type-safe builders, and so we can provide a property description, also for documentation purposes, as well as one or more example values. And we've made adding at least one example value per component property mandatory, and there's a runtime check which enforces this. And that's because we use these values to do property-based testing, and I'll talk a little bit about that in just a few minutes. And content properties are mandatory by default, but we can also define optional ones using a separate function. So here, for example, we're adding a subtitle property. Because it's optional, we have to specify its nullability as well as a default value. As a quick note, since we're using Kotlin here, it's really easy to package content property definitions as functions that can be reused on multiple components. For example, we have many components with an optional subtitle property, and so we can define the property like this, and we can use it inside of multiple component blocks like this. So this DSL is looking pretty good. We can add components, we can add properties. Now, as Laura mentioned earlier, versioning is a huge challenge of server-driven UI, and we haven't tackled it yet. Now, our design system, DLS, has been around for a while, and so we know that pretty much anything can change over time. New components can be added, they can be removed, and they can change. So that's all fine and dandy from the point of view of the design system, but working in a server-driven UI context imposes a couple of major constraints here. Number one, you have to assume, as Laura mentioned, that there are clients out in the world running all the different versions of our system because users don't necessarily upgrade. So this means that our spec needs to keep a record of what was included in each version. Number two, we can't ask internal users of Lona to update their pages every time a new version of the spec comes out. So that means that new Lona client implementations need to be backward compatible. They must be able to render pages which conform to an older version than what they support. And so to fulfill these requirements, we built in versioning into our DSL. And we enforced a rule that changes to the Lona spec, had to be additive. New components can be added, but they can't be removed. And similarly, new component properties can be added at a later date, but they must be optional. So let's look at some code again. Back to our DSL, I've got the first version of my header component, and I've already published it, so any changes would require creating a new version now. We invoke the min version function to create a version 2 block. Now we can add any number of new properties which will be scoped to this new version. So for example, here we're adding a sort of arbitrary property which controls whether or not to show a divider at the bottom of the component. We could add different one, multiple ones, and so forth. And a similar min version function can be used to scope entire components as well. So here I can add a component to version 2 of the spec. And of course, these can be combined to specify all the versioning we need, whether it's components or properties. So now we can fully define our server-driven UI specification in Kotlin. And since it's all code already, it's particularly easy to leverage the source of truth and automate as many things as possible. As we've talked about already, we knew that keeping things in sync between multiple platforms was also a challenge. And so one of the first things we did was use this Kotlin specification to generate an equivalent JSON specification so that any Lona client could consume it and test itself against it. This is what this JSON spec looks like at a glance. We generate one file per version of the spec. Excuse me. It has a list of components. Each component has a type and a list of content properties. So this is basically, so far, the exact same information that's contained in the Kotlin spec. In addition, the JSON spec also includes component instance examples. So this is the JSON format that we use to build actual screens to render on clients, following the format that Laura was talking about earlier. And so we talked about property testing when defining content property examples. And this is where it comes in. So examples generated here test all the possible example values. So this particular example here uses the short title value. The next one uses the long one. And so contents or components with more content properties or more example values can have many more entries like these. And so using the JSON spec, our current clients are able to validate their implementation. They can check that they support all the available components and the properties for any given version of the spec, and they can also check that they are indeed backward compatible. We also generated JSON schemas so that JSON Lona pages can be validated in any context. JSON schema is a standard for describing a JSON data format. We didn't come up with it. And so there are already many tools and libraries and many languages that already exist and make it possible to validate JSON against a given schema. Here's a random online JSON schema validator. On the left, we plopped in the JSON schema that is generated by the Lona spec. And on the right, we can start typing JSON following our formats, and then this website tells us if it's valid or not. So this makes it possible for both humans and backend services to validate Lona pages. Next, we generated documentation so that humans could easily read and share our specification. Here you can see a particular component. All of the properties are listed. We even have JSON examples in here for what we might use for this component or how we might use it. And all of this is just generated automatically and regenerated anytime the spec is changed. And so, of course, it would be possible to just read the Kotlin code and understand what's available in the system, but generating this separate documentation makes it more readable and makes it also easily shareable with people who might not be able or need to contribute to the Kotlin project. And so at this point, validating a Lona page is much easier than creating one. And so we created a page builder specifically for Java or Kotlin services. And right now it looks something like this. It's its own DSL. Here, instead of calling a component function to add components to our spec, we're calling component instance to create instances of components which have to already exist in the spec. Everything else is specified in a type unsafe manner. And so the type of the component is a string, so are the property names. All the validation happens at runtime, which it's good that we have validation, but it's not ideal, of course. And so right now we're working on generating a type-safe page builder. So each component will get its own function, and the properties will be passed as parameters, and it'll also manage all the versions for us. And so with this, the backend can safely and easily build Lona pages that are guaranteed to work on all the different clients. Now at this point, we've addressed 3 of the 4 major challenges. So versioning, keeping clients in sync, and documentation. And the last one is scaling. So for a while, the system worked great, but as more and more teams started to use it, the spec kept growing. It was becoming difficult to manage versions, and performance was also becoming a concern due to the number of components. And that's when we added modularization features. So instead of a single spec definition, we made it possible to define spec modules, which are effectively separate specifications. It enables teams to create their own modules. They can exclude the components they don't need. They can release their own spec versions at their own pace. As we've seen, our design system relies on reusing components. And so we made component spec definitions reusable as well. Those are defined at the top level of the spec project, like this. And they can be used and reused instead of spec modules, like this. And so that's how Kotlin helped us solve the biggest challenges of server-driven UI. We Kotlined it, or codified it. None of these sound right.
So using this system at Airbnb, we've had teams build out a lot of features with Lona. For example, this is one example. It's a screen that shows up if you log into the app before a trip, and it will suggest things for you to do on your trip. Another feature that was really successful that we think really shows just how easy this system is to use is we had a partner team that was doing a hackathon, and they came to us and they said, okay, we have one day, we want to build a feature to drive employee adoption of the beta app. So in just one day, they built out this screen that will pop up in the Airbnb app when an employee accesses it that says, hey, do you want to download the beta app and dog food our app? So they built this out in one day and launched it to a bunch of employees, and it really shows that when you get these things right, you can build features really quickly. So in conclusion, using a Kotlin DSL to power our server-driven UI framework increased our speed of iteration across Android, iOS, and web. It gave us the ability to build once and deploy instantly. It gave us better consistency across platform, eliminating differences between the spec and the clients. And it gave us better quality with our app. Now, because we have this DSL powering everything, we can be confident with our testing framework that when we launch a new feature, it will be supported on the clients we expect it to be supported on. Thanks for listening to our talk. We won't be taking live questions, but if you want to come down here and chat with us, we'll be sticking around. Thank you.